Hey, welcome back, everyone. Good afternoon. It's just afternoon. We got 4 hours ahead of us today, 12 to 4 today, 12 to 4 tomorrow. Before we dive right back into physics, I'll just take you back to page 8 of your course booklet. And I just want to highlight our schedule for the rest of the weekend and our plan of attack here the rest of the way. All right, if you go to page 8 in your course booklet, it should look like this. And so just to highlight, we're on day 2. We're not going to do 4 hours straight of physics today. So we've got 2 nominally 10-minute breaks here mixed in. And what I want to do today with the bulk of today is to get into magnetism. I'd like to spend at least 2/3 of our time today on magnetism. And in the case of magnetism, I'm going to take our time and go back through a pretty thorough review of a lot of the theory and the background concepts in magnetism, partly because I think this is a relatively new concept for a lot of people, and especially in APSC 112, you guys have only been looking at this topic for a few weeks now, as far as I know, but also because it's kind of conceptually tricky. We have a lot of intuition for things like gravity and even forces and so on, but we don't have a lot of intuition for magnetism. So we'll go through a pretty thorough, like kind of bottom-up review of magnetism. Before we get there, with the rest of our first period here, I want to cover circuits, and we'll do a handful of long answer problems on circuits and just make sure we're really comfortable with how to solve circuit problems. I would say there's a decent chance that there's a circuit question on your, a circuit long answer problem on your exam. And those types of problems, once you solve a few of them and get the pattern and get used to kind of how they work, they all kind of look the same after that. And so we'll practice a few of them and make sure we're really comfortable, and then we should be in good shape to get those marks. Just looking ahead to tomorrow's session is again from 12 to 4. And with the remainder of the time tomorrow, we're going to go through even more problems on magnetism, and then we'll get into electromagnetic induction, Faraday's law, and so on, and touch on Hall effect and eddy currents near the end tomorrow. So that's the game plan overall. Just before we dive back into circuits today, I just want to do one more long answer problem on electric potential. That's the topic we were looking at last evening. And there's one more long answer problem we should study. And I think it's a good one to study because it basically covers kind of the worst or most difficult an electric potential long answer problem could be on your exam. So to do that, let's go forwards in your booklet. We'll go to page 133 now. And from page 133, there's some room there to look at this long answer problem that you'll find on page 68 in your exam package. So page 133 in the booklet, page 68 in the exam package. And once you track that problem down on page 68 in your exam package, it should look like this on the screen. And just to highlight that this problem extends over several pages here in your exam package, just be careful. There's parts A, B, and C on the following pages there. I'll give you guys a moment to read that one over, and then we can get started on that together. Okay, so reading this one over, we've got a semicircle of radius big R, and it's carrying a positive charge per unit length uniformly along its circumference. And then there's straight sections of wire, each of length big L, and they carry a uniform charge per length of minus lambda. So just to highlight that on the screen here, the arc is uniformly positively charged, whereas the straight segments are uniformly negatively charged. Okay. And in part A, we want to find an expression for the electric potential at the origin of that arc, right at the center there. And for part A, they tell us ignore the two straight wires. All right, I'm just going to flip ahead to parts B and C. It's always good practice to read the entire long answer problem before you start, because there might be some helpful clues to help you attack the problem. And then in part B, we're going to find an expression for the potential in terms of lambda L R at point O due to both the straight wires and the semicircle. So part A is just about the semicircular arc. Part B is about that entire arrangement of wires. And then finally, let's skip forwards to part C. It's on all the way on the next page, just to read that part over. And in part C, what we'll find is that if they give us a numerical value for R, they want to know for what value of L, what length of those straight wires, does the potential equal 0 at point O. So there's a few parts to this. And back in our course booklet, let's just take a moment and redraw that diagram, just so that we have a reference point to look at. So there's our situation. And in part A, we want to get an expression for the potential at point O, just due to that arc. And there's a couple ways we could look at this, but in general, we've got a continuous surface, a continuous line of charge in the arc here. So what we're going to have to do is look at the bit of potential created at point O due to a little bit of charge somewhere along that arc. And all the points, all the bits of charge on that arc, or all the DQs on that arc, are a distance r away from point O. So we could consider a DQ there and consider the bit of potential that it creates at point O. Fair enough. Now, there's a good trick that we've done a few times with electric field problems, and that is to get an expression for DQ in terms of the geometry of this object. And the trick is to write an expression for the linear charge density, lambda. Lambda is charge per unit length, right? And that means it's the total charge on the arc divided by the total arc length of that arc. Another way of saying that is it's the infinitesimal bit of charge divided by the infinitesimal bit of arc length. And if you recall the arc length formula, a little bit of arc length is r times theta, the angle that that arc subtends. And so in our case, we could say that ds is big R d theta. R is a constant. And that lets us get an expression for dq. So dq should be equal to lambda ds, which is equal to lambda r d theta. And that d theta is a little bit of arc subtended by dq. And if you want, we could label that on our diagram. There's a little d theta subtended there. Okay, so that's an expression for the bit of charge. Let's sub that back into our expression for the bit of potential created by that bit of charge. K dq, which is lambda big R d theta, divided by big R. And so that bit of potential is K lambda d theta. All right, that's all we had to do. in part A is get an expression for the bit of potential at the center of that arc created by that bit of charge. Now in part B, we need to look at the total potential created at point O due to both the straight segments and that arc. And so if we want, we could write it something like this. The potential at point O is going to be the sum of the potential created by the arc plus the potential created by one of the straight wires plus the potential created by the other straight wire. So all three of those segments of wire are contributing to the potential. Now we're going to come to the potential created by the wire in a moment. First of all, we could get an expression for the potential created by the arc. What is the potential at point O created by that arc? Well, we'd have to add up all the dVs from part A. So we'd have to add up all the k lambda d thetas from part A. And the limits of this integration are basically to integrate around an entire half circle. So if you want, you could say that theta starts at 0 and goes all the way to pi. If you wanted to, you could have it theta starting at minus pi over 2 and going to plus pi over 2, for instance, right? But the point is that what we're integrating around is a half circle. So pi radians in total. K and lambda are both constants. And the integral of d theta from 0 to pi is pi. So that's an expression for the total electric potential created at the point O just due to the arc itself. Now, we're going to have to get an expression for the potentials created by the wires. I'm just going to pause there because I've noticed a couple of questions come in over the Q&A. Just let me catch up to these questions here. Yeah, so a couple of people have asked the same question here. Basically, don't we have to integrate our result in part A? Well, we do. We don't have to do that until we get to part B, right? Part A was to get an expression for the bit of potential. And part B, well, we have to actually integrate that. And we've got the full integral there. All right. Now, we need expressions for the potentials created by those straight wire segments. And to consider that, there's a couple ways we could look at that. But consider that if point O is the origin and one of those wires extends for its own length of big L, but it starts a distance big R away from the origin, something like that, we're going to have to get an expression for that potential. And because the different bits of charge, the different dQs that make up that straight segment are all different distances away, I guess we could call that a distance x or something, we're going to have to integrate all the bits of potential, all the dVs created by all those dQs, which are all a different distance away from the origin. So let's get an expression for the bit of arc. I guess we could call that dV wire, for lack of a better term. And that should be k dq divided by the distance from dq to point O. And that's a variable. We could call it R. Sorry, we could call it X. There's an expression for that bit of potential. And the other thing we could note is that there's a relationship between the linear charge density on that straight segment of wire and that dq in the numerator of our expression. And again, we could do that same trick that we did before, where we say lambda is charge per unit length. So it's infinitesimal charge divided by infinitesimal length. And that should give us an expression for dq that lets us relate dq to the geometry and to that variable x. So there's an expression for dq in terms of the charge density and in terms of that variable distance x. Okay. Let's plug that back into our earlier expression. So that should be k lambda dx over x. Now, the only thing we're going to have to be careful of here is that for the straight segments of wire, that charge density lambda is actually a negative quantity, right? They tell us that that line charge is negatively charged. So we just have to keep that in mind. We can either put in a negative sign now and account for the fact that the potential created by any segment of that straight wire is going to be a negative quantity, or we could keep that in mind and sub in a negative quantity at the very end. I'm going to put the negative sign in right now, and I'm just going to highlight the fact that we know that lambda for the straight wire is negative. In other words, any bit of potential created by any bit of those straight wires is a negative potential. All right, I'll just pause there. The question has come in. Yeah, there's a question just about setting up the geometry here. So looking at the picture in the bottom right corner, what we're trying to do is get an expression for the bit of potential, dV wire, created by a bit of charge dq somewhere on that straight wire. And we can set up that geometry however we like. I guess the point is that one end of that straight wire is a distance r from point O, and the other is a distance of r plus L from point O. So if you wanted to use a variable x, you just have to know what limits we're going to end up integrating over. You could set x equals 0 at the origin if you want, or you could, if you really wanted to, you could set x equals 0 at one end of the straight line. But the point is that we have to end up integrating over that full length L of that wire. So in other words, your limits of integration are going to have to match the geometry. We've chosen to denote x as the distance from point O to any bit of charge dq, and the limits when we integrate will reflect that. So just flipping over to the next page, that's an expression for the bit of potential created by a bit of that wire. And now let's integrate that to get the total potential created by one of the straight wire segments. So that's going to be the integral of the minus k lambda dx over x that we had from before. And now we have to put the right limits on here. And according to our diagram, x can vary from r to r plus L. And if we integrate along those values of x between x equals r and r plus L, we'll be integrating over the entire length, big L, of that rod, and accounting for the fact that that straight wire is a distance r from point O at its closest point. Some of these things are constants, so we can pull them out. Minus k lambda comes out, and really what we're doing is integrating dx over x from x equals r to r plus L. And the integral of dx over x is ln x, so we can sub in and get a result for that integral. Let's put our minus k lambda, and then we're basically evaluating ln x from r to r plus L. I'll just go through the steps of this math here, because sometimes evaluating integrals, getting the negative signs right, can be a little bit error prone. So ln of r plus L minus ln of r. So that's the evaluation of that integral. Now there's a trick. If you look on your formula sheet, the ln of a minus the ln of b is actually the ln of a over b. I'm going to write that over to the side here just to highlight this. This is from your formula sheet. The ln of a difference is the division of the lns, if you want, something like that. And you can find that on your formula sheet. So we could simplify that one step further. the potential due to one of those straight wires is minus k lambda ln of r plus L divided by R. All right. Let's go one step further now. We've got an expression for the potential created by the arc and the wire. So the total potential is the potential due to the arc plus, I guess it's 2 times the potential created by the wire because there's 2 of them. And so that total potential is, let's plug in our expressions. K lambda pi was the potential created by the arc, and minus 2 k lambda ln R plus L over R is the potential contributed by both of those straight wires. So there's an expression that answers part B. That's an expression that we could plug numbers into, that is the potential at point O created by an entire arrangement of charged wire. All right, and in part C, now what we want to do is calculate the value of L that would be required such that that potential at the origin is 0. I'm just going to write that in words just to restate the question. So calculate L such that V at point O goes to 0. Well, we've got an expression in general for that potential at the origin. So just rewriting it, k lambda pi minus 2k lambda ln R plus L over R. If we want that whole thing to net out to 0, we need to solve for L such that this is true. So we're gonna have to solve this equation for L. Just doing a bit of rearranging here, 2k lambda ln R plus L over R equals k lambda pi. And just doing a bit of cross multiplying and elimination. So ln of R plus L over R is equal to pi over 2, I guess, by the time you cancel the k's and the lambdas. And to solve this expression for L, we need to somehow get the L out of the argument of that ln function. And the way to do that is to exponentiate both sides. Take the exponential of both sides. E to the ln of something is that something. So we're going to take the ln of both, we're going to take the exponential of both sides. And that's going to leave us with an R plus L over R on the left side and an E to the pi over 2 on the right side. And we can go one step further and rearrange that to solve for L. So multiply the R up and bring the R over. And if we rearrange that, we'll get an expression for L. It should be R e to the pi over 2 minus R. And we know what those quantities are. They give us a value of R, 0.1. And if we calculate that out, we get 0.38 meters. Okay. This problem is kind of interesting because if you consider what's happening here, like in our expression for the potential, notice that the potential, like the very top line of algebra on the screen, our expression for that potential depends on lambda. So it depends on the charge densities on each of those objects. But notice that because the potential created by the arc is positive, we've got that k lambda pi in the first term, the potential created by the straight segments itself is negative because those straight segments are negatively charged. And in general, you could end up with either a positive or a negative value for the potential at point O, just depending on the relative length and radius of that arc. And in part C, it was the special case where what if that potential is exactly equal to 0? In other words, the positive contribution of potential from the arc is exactly equal to the negative contribution of potential from those two straight lines. All right, just checking online to see if there's any questions here. Yeah, so there's a good question about just some of the algebra about canceling terms out and so on. Absolutely, like as long as you follow the rules of math, you can work your way through this algebra however you find comfortable. So for instance, if you look at the very top line in part C, when we simplify that out, a k lambda is going to cancel from both sides, right? So that's going to simplify things. As long as you follow the rules of math, you can do it whichever way makes sense to you. There's another good question on the Q&A. Why don't the two wires cancel out? I think your question is about the two straight wires, right? I think that's what you're asking about. And this is a really good question, and I'm glad you asked. Cancel out is kind of an interesting expression, right? Cancel out is what we think of when we think of vector quantities, like a vector pointing in one direction canceling out with a vector that's equal in magnitude in opposite direction. But we're talking about electric potential. Potential is a scalar quantity. It could be positive or negative, but it doesn't have a direction associated with it. So in this problem, it's really tempting to say, well, yeah, there's a straight segment on one side of the origin, a straight segment on the other side of the origin. And if we were calculating electric field, you're right. The electric field at the origin created by each of those straight segments would cancel each other out in a vector sense. But we're not talking about field. We're talking about potential. Just consider potential as a positive or negative quantity. Remember those mesh grid surfaces we looked at yesterday? Potential is like the height of a hill. And so consider those two straight wires. They're each contributing negative potential. Meanwhile, that arc is contributing positive potential. And in part C, what we wanted to calculate is the relationship between R and L such that those would cancel each other out and result in a net potential of 0, but cancel each other out just in a scalar sense. The sum of a positive quantity and two negative quantities such that their sum is 0. I'm really glad you asked that question. And it's important because it's really easy sometimes when you're working through these problems, especially in the stress of an exam, that like, am I calculating a field or a potential? Am I calculating a vector quantity or a scalar quantity? And just be careful to kind of pump the brakes for yourself, right, mentally as you're working through those, and make sure that you're sure what you're calculating. And if you think to answer a question here in the Q&A, that's really good. Ask yourself those questions when you're at your exam. Just kind of double check your logic, right, as you go through. Yeah, and there's another related question on the Q&A that's a really good one. So are there cases where the potential cancels? Well, in part C, the potential, we could use the word cancels, but maybe more accurately, we could say the potential summed to 0. We had negative potential contributions from the two straight wires, summing, just in a scalar sense, with the positive potential contribution from the arc. And the sum of all those potentials was 0. Not a vector sum, not a canceling of vectors, but just a scalar sum of things. And if you think back to that mesh grid surface that we looked at yesterday for the dipole, you might remember that there were points on that mesh grid where the potential was positive, there were other points where it was negative, and there were points in between where it was 0. I think because there's such good discussion and question about that right now, I'm going to go back and just find that, just to point to it again, because it's a really important point. It's going to take me a minute to find this. Just bear with me one sec here. I think it's somewhere around here. There we go. There's the potential surface created by a dipole. This is not a scalar quantity. Sorry, this is not a vector quantity. This is a scalar quantity. And notice that that potential function has a very big positive value when you're very close to the positive point charge. It has a very big negative value when you're close to the negative point charge. And at other points in between, it could actually be 0. If you get really far away from that arrangement of charge, the potential is 0, but even in between those charges, near them, the potential is 0. And really what we're talking about is differences in potential that lead to differences in electric potential energy of other charges that move around in the surface of the potential created by some arrangement of charge. So this is a really good question, and I'm glad you asked. Okay, that's all I wanted to cover on potential specifically. I want to get into circuits now. And so to do that, we're going to go to page 137 in your booklet. Page 137. And that should be chapter 6. Now, I'm not going to go through a super detailed review of this chapter, partly because we looked at this in some detail a few weeks ago for midterm 2, and partly because I think when it comes to circuits, our time is better spent just practicing problems. So I'm just going to skim through this chapter really fast. We have a notion of what we call current, which is the rate of flow of charge past any point in space, and we measure that in amps. And by convention, current, when we talk about circuits, is the direction of flow of positive charges. In reality, we know that in matter, it's actually electrons that are moving the opposite direction. But conventional current is the direction positive charge would flow if it were flowing. And at a microscopic level, you can relate that current to the drift velocity of electrons as they move through that wire of a certain cross-sectional area. At a macroscopic level, you can calculate the potential drop that those electrons or those conventional current charges would undergo if they went through a resistance. And this is Ohm's law. So this relates the potential created by the battery to the potential drop experienced by charges as they move through that resistance. If you want, you could consider batteries to be like little elevators that lift charges up to a higher potential, and resistors like little hills where charges fall back to a lower potential. I used to do that for fun when I was in first year physics. And when we look at resistance and how it's created, it's really due to a property of the material that we create resistors out of called the resistivity. So that's the resistivity of a material. And the resistance is a result of using a certain material and in a certain geometry, length and cross-sectional area. That resistivity is usually temperature dependent. So different materials have different temperature coefficients for how their resistivity varies with temperature. And if you have a certain geometry of material, that means the resistance of that will vary with temperature as well. So that temperature coefficient is usually positive. Things usually have higher resistance at higher temperatures. And that's why if you're looking at your phone or your laptop or your tablet, charging usually it gets warm, right? It's getting warm partly because lots of current is flowing through it, but also because as it gets warmer, the resistance gets higher and potential drops and gains are higher. You can combine resistors in series by adding them or in parallel by adding their inverses. If resistors are in series, the current through them is the same. If resistors are in parallel, the voltages across them are the same. You can use the junction rule and the loop rule to analyze circuits, and we're going to practice that a whole bunch. Really, the junction rule is saying that all the current that enters a junction equals all the current that leaves a junction. That's actually a statement of conservation of charge. Whereas the loop rule is a statement that all the potential gains from all the batteries in a closed loop equals all the potential losses, all the potential drops across resistors from Ohm's law in that loop. And that's a statement of conservation of energy. Where does that energy go? Batteries provide energy to circuits, and that energy is dissipated as current passing through the resistors as heat. And again, that's why things like your laptop heat up when you're using them. This page here in section 6.6, we're just going to keep our eye on this. You might want to earmark this page, bookmark it for yourself. This is just a reminder of how we apply Kirchhoff's loop rule. And we're going to practice this a whole bunch. But when we're talking about resistors, so on the left side of the screen, if we're doing our Kirchhoff's loop rule accounting in the same direction the current's flowing across a resistor, that's a potential drop. If we're doing our accounting in the loop rule sense, and we cross a resistor opposite to the direction current's flowing, that's a potential gain. One way to think about that is whatever direction current's flowing through a resistor, that's like a downhill, a drop in potential across that resistor. But on the right side of the screen, looking at applying the loop rule for batteries, all that matters when we talk about batteries is the orientation of the positive and negative terminals. By definition, the positive terminal of the battery is at a higher potential than its negative terminal. We'll practice that a whole bunch here. All right. When we talk about power, power is energy per unit time. Batteries provide power to circuits. So if you calculate the current delivered by a battery and multiply by the voltage or the potential of that battery, you get the power delivered. Resistors dissipate power as I squared R or V squared over R, according to Ohm's law. And you can use that to understand how light bulbs and heaters work and power ratings and so on. And really, this is a statement of conservation of energy. Just a couple last things to review. Ammeters have zero resistance and they measure current flowing through them. Voltmeters have infinite resistance and they measure potential differences across them. And finally, one last thing, the notion of terminal voltage is the idea that if current's flowing out of a battery, in a practical battery, there's actually some internal resistance, and that results in a slight reduction in the voltage across the terminals of the battery because some of the potential created by the battery drops across its own internal resistance. So that's the notion of terminal voltage and internal resistance. All right, let's do a few problems on this to just refresh these things. Let's go to page 177 in your booklet. And there's some room there to look at the long answer problem from page 11 of your exam package. So we're on page 177 in your booklet, page 11 in your exam package. And once you find that problem from page 11, it should look like this. I'll just give you a moment to read that one over. Okay, so we've got this circuit and they tell us to assume that all these EMFs are ideal batteries. In other words, don't worry about their internal resistances. Whenever you're presented with a circuit problem, it's always a good idea to notice whether or not they tell you or assume directions of currents. If they assume directions of currents, then roll with those assumptions, use those assumptions. If you don't see directions of currents labeled on the diagram in the question, then you have to make an assumption. But in this problem, they give us this assumption for the directions of the currents. And we have to solve various things about this circuit. We have to find the increase in potential from point A to point B. So notice that there's different paths to get from point A to point B. There's lots of different routes that current could take. We'll have to figure out effectively the potential difference between points A and B. In part B, what would a voltmeter measure across that 12 ohm resistor? In part C, which of those three batteries is acting like a battery being charged? Batteries deliver power if current flows out of their positive terminal, and they absorb power, or they get charged, if current flows into their positive terminal. So if we can figure out each of those currents, I1, I2, I3, and their directions, we could figure out which of those batteries is delivering power and which of them is absorbing power. And then in part D, the power charged or discharged by the 6-volt battery itself. So to solve this, we're going to have to use Kirchhoff's rules. I'm going to go back into the booklet, and I'm going to take the time to redraw this circuit in my booklet. Hopefully you guys have already done that, but if you haven't, it's a good idea to do that. You'll notice that when I redraw circuits, I try to draw batteries with gigantic terminals on them, just to make it really clear which terminal is the positive one and which terminal is the negative one. The positive one is the one with the bigger side to it. One way to think about that is that side has more potential. It's a higher potential. Here's a 12 ohm resistor, a 6-volt battery, an 8 ohm, and a 4-volt battery, a 6 ohm, and a 2-volt battery. And in the question, they tell us to assume directions of currents. So they tell us to assume that there's a current I1 flowing like so, and that there's a current I2 flowing like so, and that there's a current I3 flowing like so. Basically, current stays the same in any branch of a circuit until it encounters a junction where it could split or combine with other currents. All right, so there's our circuit. We're going to want to write Kirchhoff's rules for this circuit. And if we do that, we'll get equations involving the unknown currents that we need to solve for, and the whole rest of the question will fall apart from that. So let's write Kirchhoff's rules. And for a circuit like this, where there's effectively like 2 loops in it, there's kind of a left half and a right half to the circuit, we could get 3 equations. We could get 2 loop rules and 1 junction rule. In other words, a system of 3 equations. So in shorthand, Kirchhoff's loop rule in the left loop, let's write that equation. Start on the positive terminal of the 6-volt battery right here, and we're going to apply the loop rule around that loop in a clockwise sense. Starting on the positive terminal of that 6-volt battery, the potential there is, by definition, 6 volts. Then we encounter a 12 ohm resistor traveling in the same direction as that current I1 is passing through that resistor. That's a drop, minus 12 I1. Then we come down the middle part of that circuit. And as we go down through the middle part of that circuit in our loop rule accounting, we encounter that 8 ohm resistor, and it has current flowing the other direction. I2 is flowing upwards through that circuit. That's a potential gain, plus 8I2. Then we cross the terminals of that 4-volt battery from positive to negative. The potential drops by 4 volts when we do that. And then we circle all the way back around to where we started, and there's no more resistors or batteries. And we get back to where we started, and the sum of all those potential drops and gains is 0. So that's one loop rule. We need to get another loop rule equation. We could use the loop on the right if we wanted to. We could also do the loop rule all the way around the outside. Why don't we try that? And the point I'm trying to make is that as long as you choose 2 different loops, you'll get enough equations and enough unknowns. So let's do Kirchhoff's loop rule around the outside. And if we do the loop rule around the outside, starting on the positive terminal of the 6-volt battery, the potential there is 6 volts by definition, minus 12 I1 as we cross that 12 ohm resistor. And now we're going to go all the way around the outside. So now we're going to go this way around. And if we do that, then we'll cross that 6 ohm resistor. up in the top right corner. And as we cross that 6 ohm resistor, we're crossing it from left to right, opposite the direction that that current I3 is assumed to be flowing. So that's a potential gain, plus 6I3. Then we encounter that 2-volt battery. From the positive to the negative terminal, we traverse across that and we lose 2 volts. And then we come all the way back around the bottom and we get back to where we started. So that's the loop rule around the outside. I'm just going to pause there and see if there's any questions about that loop rule, either of those loop rule equations, and the sense of drops and gains across those resistors. Yeah, a fair question. Why did you go around the outside loop instead of just using the right loop? You could do either one. One thing to point out, I just want to highlight something. In each of those branches of the circuit, there's a unique current flowing. And really what we're trying to do is set up a set of 3 equations and 3 unknowns. I'll just carry that thought one step further. If we write the junction rule at the bottom, junction, that would say that the current I1 plus I2 plus I3 are all leaving that junction, and there's no current entering that junction. And so taking that thought one step further, what we're trying to do is set up a series of equations, 3 equations and 3 unknowns. Equation 1, equation 2, equation 3. And back to your question, why did we go around the outside instead of just using the right loop? We could have gone around the right loop. And if you did, notice that your equation around the right loop for the loop rule would have I2 and I3 in it. As long as you pick 2 different loops, and as long as the loops you pick contain all of the different currents that you're trying to solve for, then it doesn't matter which 2 loops you pick. You're just trying to get all 3 of those unknown currents represented in this set of 3 equations, 3 unknowns. And there's another question here. What about the resistor at the top? Why is it 6I3 and not 6I1? I'm just going to highlight that on the screen here. The current I1 is only flowing in this left branch of the circuit, and the current I3 is flowing in this right branch of the circuit. So the current through that resistor, that 6 ohm resistor in the top right corner, is I3, not I1. Okay, so we've got 3 equations, 3 unknowns. And if we solve this set of 3 equations, 3 unknowns, we can solve for those unknown currents. So let's rearrange. Let's take that first equation, equation 1. And if we rewrite equation 1, we can solve for I2 in terms of I3. Just rearranging a little bit, 8I2 equals 4 minus 6 plus 12I1. And if we isolate for I2 in terms of I1, there's an equation that relates I2 and I1. All right. Let's take the second equation and do something similar. If we take the second equation and rewrite it, we can isolate for I3 in terms of I1. Now we've got I2 in terms of I1, I3 in terms of I1. And if we substitute those results back into our junction rule equation, I1 plus I2 in terms of I1 is 12I1 minus 2 over 8, plus I3 in terms of I1 is 12I1 minus 4 over 6. Now we've got one equation with one unknown. So we're just solving a system of 3 equations, 3 unknowns. We've basically isolated out the I2 and I3. We've got one equation in terms of I1, and we can solve that for I1. If you work through that math to solve for I1, you have to take a common factor and rearrange and so on. You should get I1 equals a positive quantity plus 0.204, and that's in units of amps. And the fact that when we calculate that out, we get a positive quantity, that means that the assumption was correct for the direction of I1. So in the direction that was assumed in our diagram and in our equations. Okay, so we've got a value for I1, and we could go further and calculate I2 and I3. Let's back substitute that value of I1 into our other equations. So if you back substitute, that means that I2 is equal to, I'm showing explicitly substituting in this positive quantity here. And we end up with a positive quantity plus 0.06 amps. And if you back substitute into your equation that relates I3 and I1, when you calculate out I3, you get a negative quantity, minus 0.26 amps. And that means that I3 flows in the direction opposite to the assumption that we made. Okay, so just pausing for a second, this pattern happens over and over again in every circuit question. Once you solve enough circuit questions, they all break down just like this. Write 2 loop equations and 1 junction equation. Solve that system of 3 equations, 3 unknowns for the unknown currents, and solve the rest of the problem with whatever they ask you to do. We'll get to the parts A, B, and C of this problem where we have to calculate things about the circuit. But now that we know the currents, we can solve the whole rest of the problem. The thing that I really want to highlight is that when you go and solve that system of 3 equations, 3 unknowns for the currents, if you calculate a negative number for one of the currents, and you use that quantity, that I3 in this case, in some other calculation, you have to carry that sign along with you. Just to say that in a different way, when we calculated I1, we got a positive number, and we subbed that in when we back substituted and calculated I2 and I3. If we had gotten a negative number for I1, we would have to back substitute that negative number through the other calculations. Maybe another way of saying that is, when you're studying, if you want, practice solving this series of equations for I3 first. You'll get a negative quantity, and when you back substitute into your other equations for I1 and I2, carry that negative sign in there, and you'll get the correct values for I1 and I2. Yeah, there's a question to just go over the Kirchhoff's junction rule. So the junction rule is a statement of conservation of charge, and it basically says if you add up all the currents entering a junction, it has to be equal to the sum of all the currents leaving that junction. In the diagram at the top right on the screen, I've just recreated the diagram from the question, and shown in blue there are the directions of the currents I1, I2, and I3 that they told us to use. So if you look at the diagram on the question sheet, they labeled those directions of currents. And if we consider this junction here at the bottom, right here, there's like a T-junction, right? A 3-way junction of wires meeting. All of those currents, I1, I2, and I3, are leaving that point. None of them is pointing into that bottom junction, right? Maybe saying the same thing a different way, consider the top junction. I1 is entering that top junction. I2 is also entering that top junction, and I3 is also entering that top junction. So the junction rule for the top junction would actually read the same thing. I1 plus I2 plus I3 is the sum of all the currents entering that top junction. 0 current is leaving that junction. So the junction rule is is consistent. Yeah, there's a fair question on the chat. What part of the question is all this work for? Well, if you look at the other parts of the question, we're going to have to calculate voltage drops across resistors, powers provided by or absorbed by batteries, and so on. And in order to do that, we need to know the currents through each of those sections. So we needed to solve for all these currents. Now that we have them, let's go back and calculate the things we need to calculate in the question. I'm going to flip over to my next page here. And what we want to do is first, let's calculate the voltage across the 12 ohm resistor. And the voltage across resistors, V equals IR from Ohm's law. And in this case, the current through that 12 ohm resistor is that current I1, 0.204 amps through 12 ohm resistance gives us a voltage drop of 2.44 volts. And usually when we're asked to calculate voltage, it's good to write the word volts rather than the symbol V, just because we use the symbol V for so many other things. So that's what we needed to calculate in part A. And then in part B, what we wanted to do is talk about which batteries are getting charged or providing current. And if we look at that 2-volt battery, current I3 flows into the positive terminal of that 2-volt battery. We calculated I3, we got a negative number. It means I3 points in the opposite direction we assumed on our diagram. And so therefore that 2-volt battery is being charged by the rest of that circuit. I guess that's our answer to part C, right? And lastly, in part D, we're asked to calculate the power delivered or absorbed by the 6-volt battery. So for the 6-volt battery, the power it delivers or absorbs is IV, and the current through that battery is, again, the plus 0.204. That's the current I1. Through that 6-volt battery is a power of 1.22 watts. Now, one trick that you can use for batteries if you want, if you calculate a certain current flowing through a battery and it's a positive quantity, that means the current flows in the direction you assumed. And that leads to a quote unquote positive IV or power dissipation. That battery is delivering that power to the circuit. If you plugged in a negative quantity for the current, you'd get a quote unquote negative IV or a negative power. That's power being absorbed by that battery. So for instance, if you did it for the 2-volt battery with the current I3 with a negative quantity, you get a negative power, meaning that that battery, that 2-volt battery is absorbing power, being charged by the circuit. All right, I'm just going to look back to the question here. I just want to make sure we answered everything. Oh yeah, sorry guys. Part A. I knew I forgot something. What is the increase in potential moving from point A to point B? Sorry about that. So this thing at the top is part B, right? Sorry, a little bit disorganized here. Part A, what's the potential moving between points A and B? There's a couple ways to look at that, and I'm going to flash the question back up so that we can look at that. Here's point A, here's point B. There's lots of ways to get from point A to point B through this circuit. Consider what happens if you go around the outside. if you go along that path that I've highlighted, the only thing between point A and point B is that 2-volt battery. And the positive terminal of that 2-volt battery is up here. That means point B is 2 volts higher potential than point A. So right away, just by looking at the diagram in that sense, you could say point B is 2 volts higher than point A. There's other ways to reach that same conclusion. What if you went around the other outside part of the battery, like so? The other outside part of the circuit, like so. If you do that, you have to do a partial Kirchhoff's loop rule. You have to do the loop rule, but only between points A and point B. And if you want, we can do that. You'd have a plus 6 volts crossing that 6-volt battery, minus 12I1 for a potential drop, plus 6I3 for the potential gain across that 6 ohm resistor, and that would get you to point B. And if you want to calculate that out, so around that highlighted path, let's do that. You'd get plus 6 across the battery, minus 12I1 across the 12 ohm resistor, plus 6I3 across that 6 ohm resistor. And that's the potential at point B. So one way to write that is that VB minus VA equals this. And if you calculate that out and substitute in the values of I1 and I3, being careful to plug in the negative quantity for I3, you would still get plus 2 volts. Point B is 2 volts higher than point A. And you could do the exact same thing if you wanted to go through the middle part of the circuit. I'm not going to do that calculation. You guys can practice that if you want, but you'll get the same answer that way. Often with circuit questions, there's a few different ways to answer it. In this case, we kind of looked just by inspection that around the bottom right part of the circuit was the easiest way to answer part A, but you should be able to apply a partial loop rule between points A and B and come to that same conclusion for any of the paths. There's a really fair question here in the Q&A, which is, okay, we did this circuit question and we solved for all those currents, I1, I2, I3, before we did anything else. Did we have to do it that way? Not necessarily. You might be able to answer part of a circuit question without solving for all those currents, but in general, it's usually helpful to know them. We needed to know those values of I1 and I2 and I3 to solve this entire question. So you may as well just solve for them first, and then the rest of the question just falls apart for you. All right, I'm just going to catch up with some of the questions here in the Q&A. There's a number of comments about me skipping part A, and you're absolutely right. I think we've caught up now to that. Yeah, and just to highlight, there's another question here that I want to address and highlight again. If the current was negative, would you use that negative value in all the calculations? Yeah, absolutely. You made an assumption about the direction of I3 in this case that was incorrect. You got a negative quantity for I3. And when you plug in I3 to any of your equations after that, you have to plug in the negative number. All right, I think we've caught up to all the questions in the Q&A. Let's take a look at another circuit question. The best way to get good at these is just to practice them. Let's go to page 182 in your booklet and page 59. Page 182 and page 59. Once you find the problem on page 59, it should look like this. And just be aware that that spills over to the next page as well. Just read that whole thing. There's a part C and part D on the following pages. Okay, reading this one over, we've got two light bulbs, and they're both labeled that they provide 1100 lumens, which is an SI quantity for the amount of light they generate. Bulb A is labeled as being a 75 watt bulb that produces 1100 lumens. Bulb B is labeled as a 23 watt bulb that still produces 1100 lumens. And assuming that both of these are kind of household style bulbs meant to work with 120 volt circuit, in part A, we want to calculate the current through each bulb if they were directly connected to a 120 volt supply. In part B, the effective resistance of each bulb when it's connected directly to that supply. And I'm just going to scroll to the next page. In part C, we want to calculate what the total resistance would be seen by that 120 volt supply if we connected them in series or in parallel. And the question is, which one should we connect them in? And then finally, part D on the next page. You have a friend who's got an enthusiastic interest in light bulbs that gives you a third bulb, bulb C. And there's a bunch of details here about resistivity and temperature coefficient, the resistance at 20 degrees, and the bulb heating up to 2850 degrees. What we're going to have to do is calculate effectively the temperature dependent resistivity and power of those bulbs. Okay, so let's work our way through this. Let's get back to part A. And I'm going to answer this in my course booklet. In your exam package, in this particular the year of the exam, they left enough room there on the page, but I'm just going to do this right in my course booklet. And let's get back to part A. So we're talking about bulbs, which we treat as resistors. And in general, for a resistor, the power dissipated by a resistor or a bulb is I squared R, or it's V squared over R, or it's IV. We know the power rating of these two bulbs, and we know that if they were connected to a 120 volt circuit, that they would generate each those 1100 lumens. So we can use these relationships to solve both part A and part B to get both the current through them when they're connected to that 120 volt supply, or the resistance of each of those bulbs. So with part A, we want to solve for the currents through them. The current through bulb A, if it's connected to that 120 volt supply, would be that bulb's power rating divided by that 120 volts. Bulb A is 75 watts over 120 volts would be 0.625 amps. And similarly for bulb B, we take the power rating of bulb B, divide by 120, 23 over 120, and we get the current through bulb B, 0.192 amps. In a similar way, for part B, we can calculate the resistance through each of the bulbs with Ohm's law, V equals IR. If we want to calculate the resistance from the currents in part A and the voltage, we could calculate it that way. The resistance of bulb A is that 120 volts divided by the current passing through bulb A. 120 divided by 0.625 is 192 ohms. And similarly for bulb B, bulb B is 625 ohms. Now, these equations are a little bit circular, right? You could use the power equation in part B instead of Ohm's law. Like really what we're trying to do is solve for the resistance. And notice that if you use the P equals V squared over R equation, you could solve for the resistance that way as well. These are all a little bit circular. One way to look at it is that the relationship up here that I'm highlighting at the top of the screen, that's true because of Ohm's law, right? You could sub V equals IR in there and simplify that. All right, so we've done part A and part B. Let's take a look at part C. So the first question in part C is, should we connect these bulbs in series or parallel? And for normal household circuits, we plug things in parallel. And the reason we do that is so that all the devices we plug into our household circuit see the same potential, the same voltage from the wall plug. So household circuits are wired in parallel. In other words, all devices see the same voltage. And of course, depending on the power rating of whatever device you plug in, whether it's a fridge or a blender or your phone charger, they all draw different currents. Okay, so we're talking about resistors or light bulbs in parallel. To find the equivalent resistance of those bulbs, if they're connected in parallel, we have to add up their inverses. Just be really careful at your exam when you do a parallel resistance calculation. Just remember to hit the inverse button at the end. After you sum up all those inverses, the equivalent resistance is 147 ohms. And then finally, we're on to part D. And in part D, we introduce this third bulb, and bulb C. And what we want to know is something about the way it behaves with respect to temperature. If we look at the wording of the question here, let's look at part 1 here. What we want to solve for in part 1 is the current through bulb C at the instant that it's switched on. In other words, for that brief instant as current starts to flow before the bulb heats up, while its temperature is still 20 degrees. So in part 1 of part D, we want to assume that the temperature is 20 degrees, and therefore the resistance of that bulb is still 9.5 ohms. And from Ohm's law, V equals IR, we can rearrange that to solve for the current that would flow. So that's connected to the 120 volt supply over the 9.5 ohms at 20 degrees, and we get the current that flows just at that first instant when we switch it on. It's 12.6 amps, which is an awful lot of current. And we can see why bulb C might heat up with that much current flowing through it. Now, in part 2 of part D, we're asked to calculate the resistance of bulb C once it heats up to that 2850 degrees C. So if the temperature becomes 2850, what's the resistance? And to calculate that, we have to use that temperature dependent resistance formula. So R at T is R at T naught times 1 plus alpha times T minus T naught. So T and T naught here are just two different temperatures. And we want to relate 2850 degrees to 20 degrees. So let's sub some numbers in here. R at 2850 is R at 20 times 1 plus alpha times 2850 minus 20. And we know the value of alpha as well. The value of the resistance at 20 degrees is 9.5 ohms times 1 plus the value of the temperature coefficient, 0.0045. And we can calculate the resistance of this bulb when it heats up to 2850 degrees. It's 130 ohms. Just a note here, we were given this temperature coefficient alpha, and it's a positive quantity, and it's a good way to check your answer. If the temperature coefficient is positive, then the resistance should get bigger with increasing temperature. Okay, that's part 2. In part 3, what we want to do is calculate the power delivered to that bulb. And there's a few different ways to do that. Power for a bulb is I squared R, or it's V squared over R. And it's connected to a household circuit. So we know the voltage, the 120 volts, and we know its resistance once it reaches that 2850 degrees. So let's just go ahead and plug those in. And we get 110 watts for the power that it's dissipating. And finally, in part 4 of part D, what we want to do here is calculate the length of the wire that's required to create this resistance. And for resistors, in general, rho L over A is a way to calculate the resistance of a certain geometry of a certain material with a resistivity rho. Now, A is the cross-sectional area of the wire. Usually we assume wires are circular in cross-section, and we're given a diameter here. So just expressing that cross-sectional area in terms of diameter, the diameter as it relates to the radius and the cross-sectional area of a circular cross-section should be pi d over 2 squared. D is the diameter, so that's d over 2 for the radius. And just rearranging that, 4 rho L over pi d squared. So there's an equation for the resistance of this wire in terms of its length and its diameter. And we want to solve for the length required. So let's rearrange for L. Pi d squared R divided by 4 rho. And we know what all those quantities are. We can plug right in and solve. The diameter of the wire was given. Just be really careful on your exam. If you're given quantities in things like millimeters or maybe even micrometers, you're going to have to convert to SI units. And the only thing to highlight here is this equation includes both the resistance and the resistivity, and you have to use consistent quantities. In other words, we've plugged in the resistance at 20 degrees and the corresponding resistivity at 20 degrees. You should be able to calculate the same answer if you use the resistance at 2850 degrees and the corresponding resistivity. All right, so that's a good question just to look at how light bulbs work, how power ratings work, the fact that household circuits operate in parallel with all the devices connected in parallel, and the temperature dependence of resistivity. There's a question here about why aren't the bulbs connected in series? One way to think about that is that if you connect bulbs in series, the currents through all of them will be the same. And then the the voltage across them won't be the same. And if that happens, if one of those bulbs burns out or draws too much current, then it's going to change what happens to the other bulbs. So whenever we have arrangements of light bulbs that we want to behave in a way like they do in our household circuitry with 120 volt supply, we have to connect them in parallel. All right. We've run just a little bit past when I wanted to have our break. We're going to take only a 5-minute break here. We're going to get started again at 1:25 p.m. So 5-minute break starting at 1:25. Okay, folks, welcome back. I know that was kind of a quick break. Just trying to keep us moving along here. We've got about an hour and 15 minutes to our next break. So we're going to have our next break at 2:40 p.m. What I want to do with the rest of our time today is get into a really thorough review of magnetism. And magnetism, I think you guys would probably agree, is the most difficult topic in this course. Partly because we don't have a lot of intuition for how magnetism works. And even if you studied it a little bit in high school physics, you didn't get into nearly this level of detail that you've gotten into this term in APSC 112. But the other reason is that magnetism tends to be pretty mathematically complicated. There's a lot of vector quantities, there's a lot of right-hand rules and vector cross products involved. So on top of the lack of intuition, the conceptual part of magnetism, we have all this extra math, complicated math to do. When I was in my undergrad program at Waterloo for physics, we had to take 4 courses in electricity and magnetism, and we didn't take our first one until second year. And the reason is they wanted to give us a whole bunch of calculus training in first year to get us ready for second year. And by the time we got to fourth year electricity and magnetism, the fourth of those 4 courses, it was bananas. Like it was vector calculus and crazy algebra all over the place. So the thing about magnetism that I think is tricky is that it's really shrouded in all this math. And on top of that, it's just a conceptually tricky thing. So let's go to page 188 in your booklet. And that should be the start of chapter 7. And what I want to do is go through a really thorough review and really teach you guys magnetism. And that's not to say that your profs haven't done a good job teaching you it already. It's just that because it's so new and because it's shrouded in all this conceptual and difficult math, it can be good to just kind of start from the beginning, start from basics. So what do we know about magnetism? If we look back to the history of magnetism, people have known about magnetic material for a long time, for thousands of years. Even in the 1600s, people were using the magnetic compass to navigate. So they knew there was some kind of relationship between iron and the Earth itself, and magnetic compasses were used. And a few hundred years later, scientists started really exploring electricity and magnetism. And one of the first real interesting observations about magnetism was Henrik Oersted. And he noticed that, and this was just by accident during a lecture, if he passed current through a wire in one of his lecture demonstrations, a compass needle nearby moved. Almost like somehow the current in the wire, the electricity in the wire, was influencing this magnetic compass needle. So he knew there was some kind of relationship there. And around the same time, other people, Henry and Faraday and so on, started doing all kinds of other experiments and really exploring this relationship between electricity and magnetism. There's another interesting experiment. We'll do the thought experiment a little bit later, which is that you can use a magnet to exert a force on a current carrying wire. So people were just kind of discovering this by accident. If you contrast this with something like gravity, right? Like Newton figured out gravity in the 1600s because, or it's the 1700s, I guess, because it's all around us. We see it every day. We have that intuition for how it works. But it was hundreds of years later that people started to figure out this relationship between electricity and magnetism. So just at the bottom of page 188, there's a complementary behavior between electricity and magnetism. And that is that a single moving charge or a current carrying wire experiences forces due to other magnetic fields. If you bring a magnet near a current carrying wire or likewise near a single moving point charge, you can exert a force on it. But there's also a complementary behavior, and that is that a single moving charge, or by extension, a current carrying wire, creates its own magnetic field. And the key word here is moving charge or current carrying wire. Charges need to be moving to create magnetic fields around them or to experience forces due to other magnetic fields. It's really the motion of charges that matters. All right. What we're going to do now is walk through a few of these experiments that people have done, and we'll look at basically the conclusion of each of those experiments. What did we learn about this interaction with magnetism? And as we walk through these different examples of these types of experimental observations, we're going to broadly categorize these things into one of two categories. Either the forces experienced by charges or current carrying wires due to other magnetic fields, or the magnetic fields created by those current carrying wires. So we're going to explore kind of both complements of that behavior. All right, let's start with our first experiment. In section 7.4, page 189, the force on a current carrying wire. Imagine we have a wire and we pass a current through it and we bring a magnet nearby. What we observe is that a force is exerted on the wire. And to see what's happening here, let's consider a few different cases at the bottom of the page. So in the diagram at the very bottom left, first let's do an experiment where we bring a magnet near a current carrying wire, but we don't pass any current through it. We turn off the electricity. The little blue X's here indicate a magnetic field into the page. So imagine you get a horseshoe magnet or whatever it is, and you point it at the page such that the magnetic field created by that magnet points into the page. And the orange line is the wire itself. And in the case at the bottom left, when we switch off the electricity, nothing happens. You can bring magnets near wires and nothing happens unless current flows through them. Suppose you turn on the circuit such that the current is flowing from top to bottom, downwards in the plane of the page through that wire. And you're holding your horseshoe magnet so that the magnetic field points into the page. If you do that, what you find is that there's a force to the right on that wire. And we're going to do the first of many right-hand rules now. So most of us, statistically, most of us are right-handed. Put your pen down if you're right-handed, and let's do the right-hand rule. We're going to take our fingers and point them in the direction of the current. So that means downwards in the plane of the page. It might be kind of hard to orient your hand to do that, right? I have to do some gymnastics here to do that. But if you point your fingers of your right hand in the direction of that current flowing downwards in the plane of the page, and then curl your fingers into the page in the direction that the magnetic field is pointing, your thumb points to the right. In other words, the force is at right angles to both the current and the magnetic field vector. So that's an interesting observation. Now let's look at the third picture. Suppose you switch the direction of the current. So you turn the current on, but you make it go the other way so that the current's flowing up through that wire. If you do that, what you observe is that the wire pushes to the left. There's a force to the left on it. Let's do that right-hand rule again. So put your pen down if you're right-handed. Point your fingers in the direction of that current, so upwards in the plane of the page. Curl your fingers of your right hand into the page, the direction the magnetic field vector is pointing, and your thumb points to the left. So once again, here's this interesting relationship that the force on the wire is perpendicular to both the direction of the current and the direction of the magnetic field vector. And by extension, since we know that current is made up of individual point charges, let's look at the very last picture on the bottom right. Imagine you get some kind of conductor and you have conventional current flowing upwards in the plane of the page. In other words, there's a drift velocity of that positive conventional current. That single point charge is traveling up in the plane of the page. Point your fingers in the direction of its velocity vector upwards. Curl them into the direction of the magnetic field, and that results in a force to the left. All right, so this is the first of many right-hand rules, and this is a vector cross product. The force on the wire is perpendicular to both the direction of the current and the strength of the magnetic field, and the direction of the magnetic field. And notice that in that expression, we've got I times L So I is the current through the wire and L is the length of the wire. It doesn't really matter whether you put that vector sign over the I or the L. The point is that a certain amount of current is flowing across a certain length of wire, pointing in a certain direction. And that quantity, cross product with the magnetic field vector, tells us the resulting force. So that's the first observation about magnetism. Let's flip over to the next page, page 190. If you have an interesting arrangement of wire, so that it's not like a perfectly straight wire, or if there's a weird relationship between the directions of the currents and the magnetic field vector, then to find the total force on the wire, you have to integrate all the little bits of force that would result from all the little bits of current interacting with that external magnetic field. All right. Partway down that page, page 190, I've summarized that right-hand rule. So for the direction of force on a single point charge or a current carrying wire, point your fingers in the direction of the current or in the direction of the velocity vector of that point charge, curl them into the direction of the magnetic field vector, and your thumb points in the direction of the force. So that's the right-hand rule for this type of phenomena. All right, let's take a look at a question on this. Let's go to page 217 now. Page 217. And there's some room there to look at a question from page 93 in your exam package. We want to look at multiple choice question 1 on page 93. Once you find it, it should look like this one at the top of the page. I'll just give you a moment to read that one over. Okay, so we have this wire that's got 5 different segments, A, B, B, C, and so on. There's a current flowing through that wire. Notice the direction of the current is labeled in all the sections. And we put that current carrying wire in a region where there's a magnetic field pointing in the plus Y direction. And the question is, what's the magnitude and direction of the net force experienced by that wire? So what we're talking about here is the force on a current carrying wire due to a magnetic field. And in general, that force F equals I L cross B, or the magnitude of that force is I L B sine theta. Theta is the angle between the direction of the current and the direction of the magnetic field. So what we could do is figure out the direction of the forces on each of the segments of this wire, and then find the net force. We're going to have to use our right-hand rule here. So let's look at each segment separately and look at the force exerted on each segment. Let's consider segment AB first. Current flows from A to B. So point your fingers of your right hand in the direction from A to B, in the, I guess, minus Y direction. curl your fingers into the direction of the magnetic field. The magnetic field points in the plus y direction. That's 180 degrees away. That vector cross product is 0. So there's no net force on segment AB. And similarly, let's look at segment EF. The current flows from E to F. So point your fingers of your right hand from E to F in the plus y direction. And that's the same direction as the magnetic field vector points. There's no cross product there. The angle between them is 0. And so there's no force on segment EF as well. Now let's take a look at segment BC. Point your fingers from B to C. So that's upwards, I guess, kind of in the plane of the page. And there's lots of ways to point the fingers of your right hand upwards in the plane of the page, but there's only one way to point your fingers up like that and then curl them in the plus y direction. Effectively, what we're doing is taking the right-hand rule or the cross product between the plus k hat direction and the plus j hat direction. And that vector cross product results in a force in the minus I hat direction, like so. Let's do that one more time just to practice. Point your fingers from B to C, so upwards in the plane of the page. Curl your fingers in the direction that the magnetic field points in, so to the right. And your thumb points in the direction of the force on segment BC. Let's do a similarity thing. Let's do that for segment DE now. The current flows from D to E. So point your fingers down in the plane of the page, from D to E, curl them in the direction of the magnetic field vector, and your thumb points in the direction of the force on segment DE. So that's this way. And finally, let's do it for segment CD. Point your fingers from C to D. So that's in the plus X direction. Curl your fingers in the direction of the magnetic field. So that's in the plus Y direction. Your thumb points in the direction of the resulting force on segment CD, and that's up. And if you look at the vector sum of all the different forces on those wires, you can see that there's no forces on segment AB and segment EF. There's equal and opposite forces on segment BC and DE, and the net force is upwards. These forces cancel out, and these forces are 0. Okay, so we know the net direction of that force. We know that it's upwards. And if you look at the multiple choice answers that are given, there's a whole bunch of possibilities for the Z direction. We know that it's in the plus Z direction, so it's got to be one of these 3 possible answers. Now let's figure out what that magnitude of that force is. And in this case, it should be I times big L times B, the sine of the angle between the current, which is in the X direction, and the magnetic field in the Y direction. That angle is 90 degrees, sine 90 is 1. So the magnitude of that force is ILB. And the correct answer is B. All right, I'll just pause there and see if there's some questions. There is a question about, can I show the right-hand rule? Yeah, so when I teach in person, like live in the class, this is much easier to do, right? Because I can be right there with my right hand. I'm gonna just try to walk you through those right-hand rules as we experience them. And it's really tricky for me to do on camera, just because of the perspectives and getting even the mirror images on camera, right? We're just gonna practice this a whole bunch of times and I'll talk you through it. There is a question about what's happening with segments AB and EF, and why is the force 0 on those segments? We could do, let's say, an intuitive argument first. Consider that the current in segment EF is in the same direction as the magnetic field. So if you try to curl your fingers from that direction in the plus Y direction to that direction in the plus Y direction, nothing happens. There is no curl there. There is no angle between those 2 directions. Mathematically, you can see that as well. The angle between the current in segment EF and the magnetic field is 0, and sine of 0 is 0. Similarly, for segment AB, the current in segment AB flows in the negative y direction. The magnetic field vector points in the positive y direction. The angle between those vectors is 180 degrees. Sine of 180 is 0. So you might be able to figure out with the kind of the intuition and the right-hand rule, but you can always figure it out just mathematically by looking at the angles between those vectors. Yeah, and there's another good question in the Q&A about what direction does your hand point in and so on. There is another right-hand rule that you might have learned for the direction of forces on wires, and it involves making a shape like this with your hand. It's kind of hard to see that, right? Involving the pushing on the wire. You can do the right-hand rule that way. If you learned it that way and you're comfortable with it, do it that way, okay? The way that I do the right-hand rule for forces on wires is I point my fingers in the direction of the current, I curl them into the direction of the magnetic field, and my thumb points in the direction of the force. If you learned that flat hand way for forces on wires and you're comfortable with it, keep doing it that way. That's perfectly valid. All right, just catching up to some questions on the Q&A here. I think I've addressed most of these. Just one last question here. Right, and which is, what is the direction of the net force on this arrangement? There's no force on segments A, B, E, F. There's equal and opposite forces on segments B, C, and D, E. And so the only net force is upwards, and it's on segment C, D. In other words, we're taking the vector sum of the forces on all those segments. All right, if you look back to other years' final exams, you'll find some variation of this question. And it's really just to test, are we comfortable with the right-hand rule and the magnitude of the force on a current carrying wire due to some other magnetic field? So that's one thought experiment, one manifestation of magnetism. All right, we're going to go back into the chapter and review another one. Back in your course booklet, let's go to page 191. Page 191. And once you find page 191, it should look like this. Okay, so we've learned that a current carrying wire experiences a force due to an external magnetic field. What if we create a loop of wire? In the example here on page 191, I've created a rectangular shape of a wire arrangement. So the orange thing is the wire. It's kind of like a copper wire. And I've indicated that there's current flowing in a counterclockwise sense around that rectangular shape of wire. And imagine we get an external magnetic field, we get a horseshoe magnet or whatever it is, over on the left side of your page and create a magnetic field that points to the right across the plane of the page. Let's consider the forces on each of the segments of that rectangular loop of current carrying wire. Let's start with segment 1. If there's a counterclockwise current flowing around this rectangular shape of wire, the current in segment 1 is flowing from right to left across your page. The magnetic field vector is pointing from left to right across your page. The angle between those vectors is 180 degrees. Cross product between those vectors is 0. So there's no force on segment 1. Let's look at segment 2. Segment 2 has current flowing downwards through it. Let's point our fingers of our right hand in the direction of that current. So downwards in the plane of the page. And then curl those fingers in the direction of the magnetic field. So to the right, your thumb points out of the page. You can do that one more time. Point your fingers downwards in the plane of the page, curl them to the right, and your thumb points up out of the plane of the page. There's a force out of the plane of the page on segment 2. And the way that we indicate that is with a little dot, almost like the tip of an arrow flying towards you. Now let's look at segment 3. The current in segment 3 flows to the right. The magnetic field vector from our horseshoe magnet also points to the right. The angle between those vectors is 0. The cross product between them is 0. The force on segment 3 is 0. And finally, let's look at segment 4. With our counterclockwise current around this rectangle, the current in segment 4 is pointing up in the plane of the page. Point your fingers up in the plane of the page and then curl them to the right across the plane of the page. Your thumb points into the page. There's a force into the page on segment 4. I'll just do that right hand rule one more time. Point your fingers up in the direction of the current through segment 4. Curl your fingers to the right in the direction of the magnetic field, and your thumb then points into the page at segment 4. So let's look at the net force on this rectangular loop of current carrying wire. There's no forces on segment 1 and 3, the top and bottom segment. There's a force out of the page on segment 2 and a force into the page on segment 4. So what happens if you push on something from one side and push on it from the other side? It's going to rotate. And if you put an axle through this, you can make this rectangular loop rotate. And this is how we make electric motors. We take wires and wrap them around magnets and turn the current on. And by doing that, we cause that loop to rotate. So just like there's a force on a current carrying wire due to an external magnetic field, by extension, there's a torque on a loop of current carrying wire. Let's scroll down this page a little bit and try to calculate what that torque is. If you calculate the torque, the force on each segment of wire, and you consider that there's a lever arm, half the width of the rectangle here, to each of those segments, 2 and 4, and you math that all out, what you find is that the torque is proportional to the cross-sectional area of that rectangle, the current through the wire, the magnetic field, and if you wrap n turns of this wire, in other words, if you make n identical rectangles by wrapping your wire around and around many coils, then you magnify that torque, number of coils. If there's some angle between the plane of the loop and the magnetic field vector, then what you find is that the torque is diminished. And it's really, really hard to visualize this. What I've tried to draw here is the current coming out of the page or going into the page on 2 different segments of that rectangle. And the fact that those 2 different segments of the rectangle will see a sine theta component of a force. And the easiest way to handle this is with a notion of a vector area. So the notion that the cross section of that rectangle has an area big A. And if you curl your finger in the direction of the current going around that loop, your thumb points in the direction of that area vector A. That area vector is like normal to the plane of the rectangle. And you can take the cross product A vector cross B vector to get the torque. And if we scroll over to the next page, page 192, the easiest way to handle this is with something that we define to be the magnetic dipole moment. So the magnetic dipole moment is the current multiplied by that vector area and multiplied by n if there's n loops of wire. I've highlighted here in the box how you figure out the direction of that magnetic dipole moment or that vector area. Curl your fingers in the direction the current is flowing around that loop, and your thumb points in the direction of that dipole moment vector. So expressing everything in terms of that dipole moment vector, the torque on that current carrying loop is mu cross B. Or if you prefer, you could look at it in terms of the area times the current times the magnetic field times n, if there's n loops of wire, times the angle theta between a normal vector to the loop and the magnetic field. All right. So already things are getting kind of complicated and hard to visualize, right? But just consider the fact that since a force is exerted on a current carrying wire, a torque is exerted on a current carrying loop of wire. That torque will be a maximum when the plane of the loop is aligned with the magnetic field. In other words, if that angle theta is 90 degrees. And one way to think about that is that if you have that situation where the magnetic field vector is at 90 degrees to the cross section of the loop has a huge torque that makes it want to turn. The torque is 0 when the plane of the loop is perpendicular with the magnetic field. In other words, when that magnetic dipole moment is aligned with the magnetic field. And there's an analogy here back to when we talked about electric dipoles. Remember, electric dipoles always try to rotate themselves so that they're aligned with the electric field. The magnetic dipole moment vector wants to orient itself with the magnetic field. You can look at this in terms of the energy that's stored. Magnetic fields can store energy by causing current carrying loops to rotate. And so there's limiting cases for this. The maximum potential energy stored is plus mu times B. The minimum magnetic potential energy stored is minus mu times B. In other words, if that magnetic dipole moment vector is opposite the direction of the magnetic field, there's lots of potential energy. And if the loop rotates itself such that its magnetic dipole moment vector points in the direction of the magnetic field, it's a minimum potential energy. So let's just pause for a second, because I know that that's kind of conceptual and tricky to realize, right? This magnetic dipole moment is a really powerful concept. And if you stop and consider, just kind of try to zoom out a little bit from all this physics and magnetism and everything, stop and consider a single hydrogen atom. So it has a proton and a neutron, and it has an electron going around, a single electron. That single electron is a single moving point charge. It's like a current that's flowing. Curl your fingers in the way that that electron orbits around the proton, and your thumb points in the direction of the magnetic dipole moment vector of that single atom. And if you expose that single atom to a magnetic field, the atom will orient itself such that its magnetic dipole moment points in the same direction as the magnetic field. And when you consider what types of materials in nature are magnetic, they tend to be things like iron, like really heavy magnetic elements. And if you consider the atomic structure of iron, iron has lots and lots of outer electrons that are all orbiting around the nucleus. And all those electrons are like a factor of big N magnifying that dipole moment. That's why matter is magnetic, and that's why it interacts with other magnetic fields. So this magnetic dipole moment vector is really important to understand. Curl your fingers in the direction of the current in the loop. Your thumb points in the direction of that dipole moment vector mu, and the loop will experience a torque to cause its own dipole moment vector to align with the magnetic field. Let's take a look at an example of this. We're going to go to page 212 in your booklet now. And on page 212, there's some room there to look at multiple choice question 14 from page 39. Page 212 and page 39. Okay, the one I wanted to look at is at the bottom of the page on page 39. And once you find it, it should look like this one. I'll just give you guys a moment to work through that, look at it and try to visualize the geometry of what's happening. Okay, so we've got this loop of wire, and it's in a uniform external magnetic field. There's a current that's flowing through this wire, and there's a magnetic field pointing in the minus X direction. And they tell us about the orientation of this loop with respect to that magnetic field. What we want to do is find the magnitude of the external torque that would be needed to keep this loop in static equilibrium. So first of all, first question, why do we have to apply an external torque to this loop to keep it in equilibrium? The reason is that that's a current carrying loop in an external magnetic field, and it will experience a torque due to that magnetic field. So if we figure out the magnitude of the torque exerted by the magnetic field on the loop, then we know the magnitude of the torque we would need to apply to keep it in equilibrium. Let's go ahead and calculate that. We want to calculate the torque on this current carrying loop. Now, sometimes with these loop problems, it's tricky to get the geometry and visualize it properly. There's a couple ways to visualize this. If you look at the diagram in the question and just kind of reorient yourself so that you're looking down the y-axis, that might help us visualize what's happening here. Here's the plane of the loop itself. The magnetic field vector points in the negative X direction, like so. And if we want to calculate the torque on this loop, it's the magnetic dipole moment of the loop cross product with the magnetic field vector, or the same way of saying is NAIB sine phi, where phi is the angle between those vectors. So what we're going to have to do is identify this magnetic dipole moment vector, or this area vector of the loop. And if you look at the direction the current's flowing in the diagram that's given to us, the current's flowing kind of up along the y-axis and then into the page and then back out of the page. So taking your right hand, looking at the diagram that comes with the question and curling your fingers in that sense, your thumb would point kind of diagonally into the page, perpendicular to the plane of the loop. In other words, the dipole moment vector of the loop points like this. I'm just going to pause there and see if there's any questions about that direction of the dipole moment vector. Yeah, I figured there would be questions. So I'm going to try to describe that again. Take your fingers of your right hand and point them from D to A on that rectangle. So that rectangle, see how it's labeled A, B, C, D? Point your fingers from D to A. So kind of up, right? In the positive Y direction in the diagram with the question. And then point them, curl them from A to B, curl them kind of inwards diagonally along that segment AB, right? And as you curl your fingers around, what you get the sense is that your thumb is pointing perpendicular to the plane of the loop, diagonally into the plane of the page. And in the diagram that I've drawn on the screen here, I've reoriented us so that we're looking down the y-axis at the top edge of the plane of the loop, almost like we're looking down at a door, right? The top edge of a door as it swings. And in that diagram, the way the current is flowing in that diagram is along segment A to B. So this is A and B. The current's flowing like that along segment AB. And likewise, out the bottom plane of the loop, which you can't see here, right? Because we're looking down at the top of the loop, but from C to D, the current's flowing back the other way, right? So what we're doing is a right-hand rule, curling our fingers in the direction the current's flowing around that loop. And our thumb is pointing in the direction of the dipole moment vector, the mu. All right. So what we really need to do to solve this and calculate the magnitude of this torque is identify the angle between that mu vector and that b vector. And so to do that, I'm just going to draw one more diagram to try to isolate that out. Here's a reference line that is the z-axis. And here's a reference line that is the plane of the loop. And there's a 35-degree angle here, like so. Our magnetic field vector points purely in the horizontal direction. And our magnetic dipole moment vector, by definition, is perpendicular to the plane of the loop. And so we're just going to have to do a little bit more geometry here to figure out this angle. That's 35 degrees. So that's 55 degrees. And that's 35 degrees. The angle between mu and b is 35 degrees. So we can take that one step further and we can calculate the magnitude of this torque now. And let's plug in the numbers that we've got. There's one loop of wire here. It's carrying a current of 5.5 amps. The cross-sectional area of this rectangular loop is 30 centimeters by 40 centimeters, 0.3 times 0.4. That's the area. The magnetic field is given in units of Tesla, 2.9 Tesla, and there's a 35-degree angle between the magnetic dipole moment vector and the magnetic field vector. And so we can calculate the magnitude of that torque. If we work it out, we get 1.1 Newton meters. That's the magnitude of the torque exerted on that current carrying loop by the magnetic field. And if we want to keep this loop in static equilibrium, we have to apply an equal and opposite magnitude of torque. So that's the magnitude of the torque we would need to apply, and that matches up with option B. I'll just pause here and catch up on the Q&A. Yeah, so there's a good question here, just going over the direction of the dipole moment vector again. So I'm just going to scroll up here. And again, this is so much easier if I'm teaching live. If I'm in front of you guys in a classroom, you guys can watch me do all kinds of contortions with right-hand rules and so on. It's really tricky on a camera like this, just with the perspective. But looking back to the question, okay? So as I walk you through this, look back to the question. Focus on the vertices of that rectangle, A, B, C, D. You see in the diagram? Point your fingers from D to A. So in the positive Y direction on the diagram. and now curl them from A to B. In other words, let your fingers curl in the direction that that current is traveling as it goes around that rectangle, from A to B to C to D, all the way around. And as you curl your fingers like that, you find that your thumb points diagonally into the plane of that loop. By definition, that magnetic dipole moment vector, mu, is perpendicular to the plane of the loop. And in this case, it took a little bit of contortions to visualize what angle is that magnetic moment vector mu relative to the magnetic field vector B. And that's something we have to do every time because we have to identify this angle phi. We have to identify the angle between those two vectors so that we can evaluate that cross product. And one other question here, and that is, where does this value of n come from? So first of all, what is n? N is the number of loops of wire. So this is a single loop of wire, right? It's just one wire that's been drawn out into a rectangular shape. But if you did that n times, let's say n was 100, right? Let's say you got your wire and you stretched it around and around, you made 100 like rectangles on top of each other, well, then the torque would be 100 times bigger because the forces on each of those wire segments would be magnified 100 times over. So n is the number of loops of wire. And in this problem, there's only one loop. And so n is equal to 1. All right, hopefully that answered your questions. Yeah, so there's a 35, there's a question here, what angle is that? There's a 35-degree angle between the plane of the loop and the z-axis. That's given in the question. You can see that in the question. And I've just kind of visualized that coordinate system so that we're looking down at the top of the plane of the loop. And you can see that there's a 35-degree angle between the mu vector and the b vector. Just to clarify, that's a 30, sorry guys, that's a 35-degree angle. All right, so that's the torque on a current carrying loop due to a magnetic field. All right, let's go back in your booklet. We're going to go to page 193 now, back into the chapter and review another one of these concepts. Page 193. And once you find page 193, section 7.7, it should look like this. Okay, so we've learned about two manifestations of magnetism, two experiences in nature. Current carrying wires experience a force in a magnetic field, and likewise, loops of current carrying wire experience a torque. But we know that current itself is made up of a bunch of individual moving charges. So it follows that a single moving point charge also experiences a force due to a magnetic field. Any particle that has a charge that's moving will experience a force due to a magnetic field. This is the relationship for the force on that moving point charge. You can see that it's a vector cross product, or its magnitude would be q v b sine theta, where theta is the angle between the velocity and the magnetic field vectors. That's a vector cross product. You can use the right-hand rule to evaluate that. Point your fingers in the direction of the velocity vector of the charge, curl them into the direction of the magnetic field vector, and your thumb points in the direction of the force on a positive point charge. And if you have a negative point charge, the force is in the opposite direction. So this is yet another right-hand rule to remember. V cross B, and your thumb points in the direction of the force. Now, if you rearrange this a little bit and look at what happens when a particle is traveling in a magnetic field region, what you'll find is that the force is perpendicular to the velocity. That vector cross product says force is perpendicular to velocity. And as a result, we get circular motion. And I think I've tried to show that on the next page here. I'm just going to scroll over to the next page, and then we'll scroll back and look at those last two equations. On page 194, just at the very top of page 194. So here's a single proton, and this proton is traveling. Let's say it's traveling straight up in the plane of the page. And let's say we put a magnet nearby such that we create a magnetic field vector that points into the page. So those little X's denote that there's a magnetic field into the page. Let's do the right-hand rule for the direction of the force on this proton if it's traveling upwards in the plane of the page. So V upwards curled into B into the plane of the page results in a force that points to the left on that proton. And if the force is perpendicular to the velocity, then that results in circular motion. The proton will start curving. And let's look at another case. Let's look at the case where the proton is traveling from right to the left in the plane of the page. Point your fingers in the direction of that velocity, so from right to left. Curl your fingers into the plane of the page, and that results in a force downwards on that proton, like so. Again, the force is perpendicular to the velocity. The proton keeps curving. And let's look at one other case. Let's say the proton's over here and it's traveling downwards at that instant. So tangent to that circular path, but at that instant downwards. Point your fingers downwards, curl your fingers into the page, and sorry, this is really contorting me. Curl your fingers into the magnetic field, into the page, and you get a force to the right. In other words, the force is perpendicular to the velocity, and this particle travels in a circular path. And if you use what we've learned in APS-C 111 about centripetal force, the net force on a particle moving in a circular path. So F equals QV cross B. The magnitude of that force is QVB sine theta, which goes to 1 because V and B are perpendicular to each other. The net force on this particle is QVB, and that's equal to mv squared over r. If you rearrange this, the radius of the circular path is mv over qb. So this is uniform circular motion. That magnetic force, and by extension, that magnetic field, is accelerating that proton by changing its direction, but it's not doing any work on that proton. It's not changing its kinetic energy. It's just changing its direction of motion. Let's scroll back to the previous page, and just to summarize that, so here's the formula we derive from uniform circular motion for the radius of the circular path that's followed by a particle who's traveling with a velocity that's perpendicular to an external magnetic field. And by extension, remember speed equals distance over time. The circumference of a circle is 2 pi r. You can calculate the amount of time that it takes to go around that circle once. And that's the period of that circular motion. All right, so that's the force on moving point charges and the circular motion that results. Let's take a look at an example of that. Let's go to page 215 now in your booklet, 215. And there's some room on page 215 to look at this multiple choice question 6 from page 76. We're on page 215 and page 76. And the question that I wanted to look at is question 6 on page 76. It should be the one at the top of the screen here once you find it. I'll give you guys a moment to read that one over. Okay, so as we read this one over, we've got 5 different particles. They're labeled A through E. They all have the same mass. Okay, they enter a region with a uniform magnetic field directed into the page. So it's really hard to see from the diagram in the question here, but there's almost like little X's in the background here. So there's a magnetic field into the plane of the page uniformly throughout this space. All of these particles enter with the same velocity, but they all have different charges. Each of A, B, C, D, E might have different charges. And what we want to do here is rank these charges from most negative to most positive. Okay, and when we look at the diagram that comes with the question, you can see the trajectories that each of these follow, right? So here's particle A. It curves to the right and it has a pretty big radius. And for comparison, here's particle C and it curves to the left and it has a pretty small radius. So there's something going on here, moving charged particles in a magnetic field, and they experience a force. That force is at right angles to the velocity. And we know that there's a relationship between the charge to mass ratio and the radius. R equals mv over qb. So by looking at those equations, what we can tell is the sign of the charge will dictate whether the charge curves to the left or the right. And the size of the radius of the circular path will indicate the magnitude of the charge. So let's work through these things one at a time. First of all, let's consider the signs of the charges and the relative directions. So let's consider particle A. Let's say it enters with a velocity vector VA, tangent to that arc, but pointing up as it enters that field region. Take the fingers of our right hand, point them in the direction of that velocity vector up in the plane of the page, curl our fingers into the page in the direction the magnetic field goes in, and our thumb points to the left. So a positive point charge would accelerate to the left and it would curve to the left. But we're shown in this picture that particle A curves to the right. So here's the direction of the force on a positive charge A, but charge A must be a negative charge. The force on a negative QA would be to the right. So just from the right-hand rule and that vector cross product, we can tell the sign of the charges. A must be a negative charge. And since A curves to the right and it's negative, look at the other charges. Notice that charge D also curves to the right. So just by combining those facts together, we know that QA and QD are negative. And similarly, QB and QC are positive. And notice that particle D just goes straight. Particle D is like not influenced at all by that magnetic field. Particle D must be neutral. It might be a neutron or something. Yes, there's a question that just came in here. I just want to highlight something, guys. I was typing too fast, right? QD is not negative. It's QE that's negative. QD is neutral. D is undeflected. It just goes right through, straight through. Okay, so we figured out from that right-hand rule and that vector cross product what the signs of all these charges are. Now let's look at their magnitudes of charge. Look at the bottom left corner. So R equals mv over qb. All these particles have the same mass m. They all enter this magnetic field region with the same velocity or same speed v. They're all in the same magnetic field region, B, so the bigger the charge, the smaller the radius. And vice versa, the smaller the charge, the bigger the radius. So that means that A and B are smaller in magnitude than C and D. You could capture that something like this if you want. The magnitude of QA is less than the magnitude of QB. Sorry guys, QD. Oh gosh, sorry guys. Having a little bit of tablet dyslexia here. D is neutral. A and B have the biggest radius, therefore they have the smallest charge. The magnitude of QA is less than the magnitude of, let's say, QE. And similarly for B and C. So if we put all those facts together and rank these things from most negative to most positive, E is the biggest, most negative charge. A is also negative, but its magnitude of charge is a bit smaller. D is neutral. B is the next most positive charge. And C is the biggest positive charge. And so combining all that stuff together and looking at the multiple choice options, the correct answer there is this one, D. Some variation of that question shows up pretty much every year. And it really boils down to using the right-hand rule to figure out the direction of the force on that moving charge. Just be careful of negative point charges. The direction of the force on a negative charge is opposite the direction of the force on a positive point charge. And using that equation for the radius, you can see that the radius is inversely proportional to the charge. Another way of saying that is that it's proportional to the mass to charge ratio. And this is how a mass spectrometer works. If you've ever used a mass spectrometer in one of your chemistry labs, or if you go into that field later, you almost certainly will. Mass spectrometers do exactly this. They get charged particles, or they ionize particles to make them charged. They accelerate them through a potential difference. They get them moving at a known speed in a region of a known magnetic field, and then they measure how they curve. And by measuring that radius, you can figure out the mass to charge ratio of that particle. All right, I'll just pause there and look at the Q&A, catch up there. There's a question, how did we come up with the radius equation? We did that back in your course booklet, and I'll flip back there in a moment, but it's the notion that the magnetic force on this moving point charge is perpendicular to its velocity. In other words, it's the net force in uniform circular motion. So we used mv squared over r, the centripetal force, and rearranged to solve for the radius. I'll show you that in just a moment when we flip back into your booklet. There's a question here about A and E. You're right, A and E do have different radii, and therefore they have different charges. So if you look at the equation in red on the bottom left, the radius is inversely proportional to the charge. A has a much bigger radius than E, and that means that A has a smaller charge than E, magnitude of charge at least. And that's what we've captured in our answer. All right. Just taking a look at the time here. It looks like we've got time for one more question before our next break. Let's go to page 207 in your booklet. Let's go to page 207. And there's some room there to look at. Sorry, guys, I'm just catching up here. Page 207. There's some room there to look at multiple choice question 9 on page 28. We're on page 207 and page 28. Okay, once you find question 9 on page 28, it should look like this at the bottom of the screen. I'll give you guys a moment to read that one over. All right, so suppose we have an ion source. It's producing lithium-6 ions. And we're given that they have a positive charge plus E and a given mass. These ions are accelerated by a potential difference of 10 kilovolts, 10 kV, and they pass horizontally into a region where there's a uniform vertical magnetic field. Okay, so ions get accelerated, they're traveling horizontally, and they enter a region where there's a magnetic field pointing vertically upwards. What we want to do is calculate the electric field that we would need in order for those ions to pass through undeflected. All right, I'm going to go back in our course booklet and try to draw a picture to capture what's happening here. So there's a couple of things happening. First, there's a potential difference. And that potential difference accelerates these things. It's a 10 kilovolt, so 10 times 10 to the 3 volts potential difference. And this is our lithium-6 ion that's presumably starting from rest, and after it accelerates through that potential difference, it's got a certain speed, v. So that's part of the experiment. And then those ions are traveling horizontally, and they're entering a region where there's a magnetic field pointing vertically. And what we want to know is, what electric field do we have to introduce in order for those ions to pass through undeflected, in order for them to not curve, in other words. So there's two parts to this question. First, we have to figure out what that speed v is. We can use conservation of energy and electric potential energy to figure that out. And then we have to figure out what's happening in this magnetic field region and how do we make those ions pass through undeflected. Let's treat that in two parts. So first, let's figure out what that speed v is. And we can use conservation of energy to do that. The Q delta V, in other words, the electric potential energy of accelerating that ion, results in a certain final speed, half mv squared. And we can rearrange and solve for that speed, v. It's the square root of 2q delta v divided by m. And we know what those quantities are. So let's go ahead and calculate that. The charge on this lithium-6 ion is plus E, so plus 1.6 times 10 to the negative 19. It's being accelerated through a 10 kilovolt potential difference. We're given its mass. And when we calculate the resulting speed, we get 5.66 times 10 to the 5 meters per second. So that's the speed that our lithium-6 ion is traveling at when it enters this magnetic field region. Okay, great. So now let's focus on the right side of our diagram. Now we've got a lithium-6 ion traveling to the right horizontally. It's in a region where there's an upwards magnetic field B. And what we want to calculate is the electric field necessary to make that particle travel in an undeflected way. So just a little thought experiment here. Let's say there wasn't any other electric field. Let's say it was just a magnetic field region. What would happen to this proton? We have a moving charge in a magnetic field, point our fingers in the direction of V, curl them in the direction of B, and we would get a force perpendicular to both of those out of the page. And that particle would travel in a circle. It would be deflected. So how do we prevent that from happening? We need to create an equal and opposite force due to an electric force. Remember, there's a force on point charges. So just in terms of the magnetic force, there would be a magnetic force out of the page. Let's call that Fm. And we need to create an equal and opposite force into the page. We need to create an Fe that points into the page to oppose that magnetic force. And just writing down the relationships here, I'm just going to go scroll to the bottom here for a sec. The force on that point charge is QV cross B due to the magnetic field. But if we also introduce an electric field, the force on a point charge due to an electric field is QE. That's the electric field, the electric force on that point charge. So notice something about this equation. If you have a point charge in an electric field, it experiences a force no matter what, whether it's moving or not. If you have a moving charge particle in a magnetic field, it experiences a force perpendicular to both its velocity and the magnetic field. If you have both an electric and a magnetic field, there's going to be some net force that's the vector sum of all those. And this equation is what we call the Lorentz force equation. And if we want this particle to pass through undeflected, undeflected means that the magnitude of that net force is 0. In other words, that means the magnitude of the electric force is equal to the magnitude of the magnetic force. In other words, QE equals QVB. So the electric field we need is V times B. We know what the speed is, we know what the magnetic field is, so we can just calculate that straight away. 5.66 times 10 to the 5. Multiplied by the magnetic field, 1.2 Tesla. And we need an electric field strength of 6.8 times 10 to the 5 volts per meter. And that's answer C. I'm just going to pause there and see if there's any questions about that one. Okay, so you might have experienced questions like this when you're working through your workbooks. This arrangement is what we call a velocity selector. And that's where we deliberately set a certain ratio of electric field strength and magnetic field strength. We orient those fields perpendicular to each other. And then when we fire ions into that field region, only ions with a specific speed will pass through undeflected. and that's governed by the equation at the bottom that we derived. In order to get equal magnitude forces from the electric field and the magnetic field, there's a certain relationship that has to be maintained between the particle speed and the electric and magnetic fields. Only particles with a certain speed will pass through undeflected. And just one more time for the right-hand rule for what happened there, let's just take a look at the forces that are happening in that velocity selector. So first consider the magnetic force, the force on the moving point charge due to the magnetic field. We're told that the ions are traveling to the right horizontally. We're told that there's a magnetic field upwards vertically. So point your fingers to the right, curl them up, and you get a magnetic field, you get a magnetic force out of the plane of the page. And in order for those particles to pass through undeflected, we need an electric force, a resultant electric force into the page. And the magnitude of that force has to be QE. All right. There's a question, why is it just QV cross B? Maybe instead of QVB sine theta, you mean? I think that's what you're asking. The reason in general, the magnetic force on a moving charged particle is QV cross B. The magnitude of that would be QVB sine theta, but V and B are perpendicular to each other. In this case, the velocity vector is to the right and the magnetic field vector is up. So sine theta is 1. There's another question here. How are we able to find the field strength without first knowing the magnetic field? I'm pretty sure we were given the magnetic field in this question, right? Let's just double check. Yeah, we're told in the question that there's a known magnetic field in this region. Sorry, we're on page 28 here. Let me just scroll back there to highlight that. And I'll just leave that part highlighted. We're told in the question what the magnetic field is, and what we want to calculate is the corresponding electric field that would be necessary to make these ions pass through undeflected. So this is our velocity selector. Okay, just checking the time here. It's 2:45. We're going to take a 10-minute break, and we're going to get started again at 2:55. All right, I'll see you guys in 10 minutes. Okay, guys, welcome back. Just before 3 o'clock here, we've got just over an hour to go before we wrap up today at 4 o'clock. What I want to do with the rest of the time today is to just work our way through continuing to review magnetism and both the effects of magnetic fields on things like current carrying wires and loops and moving charges. But what we'll get into in this next period is where magnetic fields come from. How do we calculate the magnetic field created by currents? Just before we dive back into physics, I just want to do a really quick poll with you guys here. I'm just going to launch a poll here just to check in with you. Just 2 questions. Let me know how you find the speed at which we're going through this material right now. Okay, awesome. Thanks for helping answer that. There's a few people that say too fast, a few people that say too slow. The majority of people are saying just right. That's kind of what I'm aiming for. The tricky thing with magnetism, right, is it's difficult in different ways for different people. Some people can visualize what's happening, but the math is tricky. Other people are really good at the math, but it's like conceptually what's happening here. And so I've learned over time teaching this course, the best way to go through magnetism is kind of nice and slow and just make sure we reinforce each of the different concepts. Just going to launch one more question here in the poll. And if you could just help answer this one, how's the level of difficulty with what we're working on right now? Okay, that's great feedback. Thanks, guys. Looks like we're kind of nailing it with the level of difficulty. And again, what I've learned is if I pick certain multiple choice questions just to help highlight and reinforce the concepts in this part, then we're in much better shape when we get into the long answer problems on magnetism, which tend to be way more mathematical. So right now we're just working our way through reviewing the concepts. We're using multiple choice questions to do that. And we'll continue with that for the next hour or so, up until 4 o'clock. We've got a couple more concepts to review. Back in your course booklet, I just want to take you back to page 194. Let's go back to page 194. And just starting at the top of page 194. So what I've shown there is the circular path that a single moving point charge would travel on if it experiences an external magnetic field. And right at the top right of that page, I've annotated the force acting on that point charge. What is the theta, the sine theta in that equation? This is a vector cross product. You remember the mathematical definition of a vector cross product? A vector crossed with another vector, the magnitude of that is the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by the sine of the angle between the vectors. So this theta is the angle between the velocity and the magnetic field vectors in this case. That comes from the mathematical definition of the vector cross product. And taking that one step further, in the case where the velocity vector is perpendicular to the magnetic field vector, we'll get perfect uniform circular motion like we see in the diagram here. And if this is uniform circular motion, then the net force due to this magnetic force on the charge is equal to mv squared over r. That's uniform circular motion. And we can rearrange that and solve for the radius of that circular path. So that mv over qb. If you look at your formula sheet, that formula that I've highlighted is on your formula sheet. So you can just use it for moving charges traveling perpendicular to magnetic fields, but it's really easy to derive. It's the net force, the centripetal force that results from a magnetic field acting on a moving point charge. Okay, let's just scroll down to the bottom part of page 194, section 7.8. And just before the break, we looked at this example of what we call a velocity selector. And the idea with the velocity selector is that if we have a particle traveling through a region where there's a combination of an electric field and a magnetic field present. So in this diagram, I've arranged things such that there's an electric field pointing downwards in the plane of the page. There's a magnetic field pointing into the page. And if you have a velocity vector from left to right across the page, there will be forces, magnetic forces and electric forces on this moving point charge. If the velocity vector is from left to right and the magnetic field vector is into the page, point your fingers from left to right, curl them into the page. That results in a magnetic force upwards on that moving point charge. And likewise, if there's a charge, whether it's moving or not, and there's an electric field pointing downwards in the page, then a positive point charge will experience a downwards electric force. Those electric and magnetic forces will be equal and opposite for a certain value of the speed of the particle. And we can calculate that out. The condition for that particle to pass through undeflected that's the condition for a velocity selector to work. The relationship between the electric and magnetic field strengths that selects a certain speed of particles. All right, so that's what we call a velocity selector. Okay, we're going to move on now and review where magnetic fields come from. So far, we've looked at effects of magnetic fields on things. We've looked at the force on a current carrying wire, or the torque on a loop, or the force on a moving point charge. Now we're going to look at where do magnetic fields come from in the first place. Let's go to page 195. Section 7.9 on page 195. So where do magnetic fields come from? In order to calculate the magnetic field created by a current, we need to use something called the Biot-Savart law. And what the Biot-Savart law tells us is the little bit of magnetic field created by a little bit of current traveling in a certain direction. This constant mu naught is something we call the permeability of free space. This is a constant of nature. And in the Biot-Savart law, what we're doing is trying to figure out the magnetic field some distance away from that bit of wire that's creating the magnetic field. And there's this weird vector cross product that's happening up in the numerator here. And I just want to highlight something for you. There's two different ways the Biot-Savart law can be expressed. I'm showing two different forms of the same equation on this page here. And just take note of something. In the top equation, we've got r hat in the numerator and r squared in the denominator. And in the bottom equation, we've got the vector r in the numerator and r cubed in the denominator. And either of those versions of that formula works because the definition of r hat is a vector divided by its length. Okay. So this takes a little bit of work to try and visualize what's happening. And down at the bottom of the page, I'm trying to indicate what's happening here. Imagine you have a little length of wire. I just noticed that in this diagram, I've called that little length of wire ds, but I could have equivalently called it dl. Sorry about that, the little inconsistency there. But what is that? That's a little vector in the direction of a little bit of current flowing in a wire. What we want to do is calculate the magnetic field created by that little bit of current, that little section of wire. And we want to know what that magnetic field looks like at 2 points in space on either side of this wire. The Biot-Savart law helps us figure that out. And it says, draw a vector that points from that little bit of wire to the point in space where you want to calculate the magnetic field. So that's what that r vector is, either the r hat or the r vector itself in the Biot-Savart law. Now, it's a little bit tricky to visualize, but I'm going to show you another right-hand rule. What I want you to do is point your thumb in the direction of the little bit of wire that's creating this magnetic field. Point your thumb along the wire in the direction of that ds vector. Curl your fingers of your right hand around the wire. Imagine a circle that kind of comes out of the page and then goes back into the page on the other side of the wire. What happens is this wire creates a magnetic field vector that literally circulates around it. So if we consider the little bit of wire ds here, that creates a magnetic field that's out of the page everywhere, quote unquote, above the wire in the plane of the page. So there's a magnetic field pointing up out of the page everywhere above that wire. And if you curl your fingers back over, there's a magnetic field vector that's pointing into the page everywhere below that wire. It's really hard to visualize that, especially on a camera here. If I were live in front of you guys, it would be much easier. I've tried to visualize that on the next page, page 196, to make it a little simpler. This is a different view of the same situation. Imagine this is our wire, and imagine the wire is going perpendicular to the plane of the page, in and out of the page, such that the current is flowing into the page. If you use that Biot-Savart law to calculate the magnetic field created by that long straight wire, take your thumb and point it in the direction of the current into the page. Curl your fingers around your thumb. And what you find is that there's a magnetic field tangent to a circle that's concentric with that wire. And if you get farther away from the wire, that magnetic field gets smaller. And if you use the Biot-Savart law to calculate the magnetic field created by a long, straight, current-carrying wire, what you find is that the magnetic field gets weaker and weaker the farther you get from that current-carrying wire, with a 1/r relationship. In other words, currents create magnetic fields. The strength of the magnetic field is proportional to the current and inversely proportional to how far away you are from that current. So that's the magnetic field created by a long straight wire. And that formula can be derived from the Biot-Savart law. And to get the direction of that magnetic field, point your thumb in the direction of the current and curl your fingers around the wire to tell you the direction that the magnetic field vector kind of circulates around the wire. So that's the Biot-Savart law for a long, straight, current-carrying wire. We're going to take a look at an example of that to help us visualize it. Let's go to page 213 now. Page 213. And there's some room there to look at this multiple choice question 8 from page 57. We're on page 213 and page 57. And the one that I want to look at is right at the top of that page. Multiple choice question 8, it's at the top of the screen here. I'm going to give you guys a moment to read that one over, and then we can go through it together. Okay, so what they're asking us to do here is to figure out the direction of the net magnetic field at point C. Point C is over here. And we need to look at the diagram, the picture that comes with the question, to really understand what's happening. There's two wires in the plane of the page. Wire 1 has a current that flows from left to right. And wire 2 has a current that flows downwards in the plane of the page. And the question is, what's the magnetic field created by this arrangement of wires at point C? Okay, so let's pause for a sec before we dive in. We know that long, straight, current-carrying wires create magnetic fields. The strength of the magnetic field is proportional to the current and inversely proportional to the distance from the wire. We can write that down. Uh, 2 pi r. And we know that we can use the right-hand rule to tell us the direction of the magnetic field created by a current-carrying wire. Here we've got 2 current-carrying wires. Let's figure out the field created by each of those wires. And then we'll have to take the vector sum at point C to find the net magnetic field. I'm going to use different colors here to help make this more clear. So here's wire 1. A current I1 flows from left to right. Let's find the magnetic field created by I1. Point your fingers in the direction of that current I1. Curl your fingers around your thumb. Everywhere above that wire I1, there's a magnetic field vector B1 that points out of the page. And everywhere below that wire I1, there's a field vector B1 that points into the page, no matter where you go. Now, if you go farther away from wire I1, the strength of that field gets smaller and smaller. But everywhere above I1, that field direction is out of the page. Everywhere below that wire I1, that field direction is into the page. Now let's do a similar exercise for wire 2. I'm going to color that in blue. Let's call that I2. I2 flows downwards. Let's figure out the magnetic field created by that current I2. Point your thumb in the direction of that current I2. Curl your fingers around your thumb. Everywhere to the left of wire 2, there's a magnetic field vector B2 into the page. And everywhere to the right of wire I2, there's a magnetic field vector B2 out of the page. We're interested in what's happening at point C. And at point C, we can see that the field from B1, the field B1 from the wire I1 is into the page. And at point C, the field B2 from the wire I2 is also into the page. Those two magnetic field vectors add in a vector sense, and the net magnetic field at point C points into the page. So the correct answer here is B. At point C, the net magnetic field points into the page. Really what we're doing here is a vector sum of two magnetic field vectors. We have to use the right-hand rule and the Biot-Savart law to calculate the strength and direction of the magnetic field created by each wire, and then do a vector sum. Every year there's a variation of this problem on the exam. If you look through the previous years, you'll find there's other similar types of questions like this. There's even questions where sometimes the magnetic fields are pointing in opposite directions. So just to highlight that scenario for you, consider what's happening up in this quadrant up here, where the field B1 due to I1 is out of the page, but the field B2 due to I2 is into the page. Those two vectors are opposite each other. And depending on the values of the currents and the distance from each wire, one of those vectors might be bigger than the other one. and you could calculate the net magnetic field by doing a vector sum, a subtraction in that case. And notice a similar thing is happening down here in this quadrant, where those vectors are opposite each other. And depending on the strengths of the currents and the distances from the wire, one of those vectors might be bigger or smaller than the other. Look up in this quadrant, both of those magnetic fields are pointing out of the page. So up at point A there, in that quadrant, the net magnetic field is out of the page. It's a vector sum out of the page. All right, so that's a brief review of magnetic fields created by long straight wires. Just catching up on the Q&A here. Yeah, there's a question about what about the magnetic field at point B? So that's down in the bottom right corner. And yeah, we just kind of went through that, and the notion that those magnetic field vectors are pointing in opposite directions. If those currents are equal, and if the distance between each wire and point B is the same, then those fields should cancel at point B. All right, so that's the magnetic field created by a long straight wire. Let's go back into your course booklet again. We're going to go to page 197 in your course booklet. There's one last magnetic effect that we need to review. We've learned that a current carrying wire in an external magnetic field experiences a force. And likewise, we've just learned that current carrying wires create their own magnetic fields around them. So what happens if you get two wires near each other? The field created by one of those currents exerts a force on the other wire, and vice versa. Now, we could go through the right-hand rule, it's actually a double right-hand rule, to figure out the direction of that force. So for instance, in this picture, we've got two currents flowing, let's say, kind of left to right in the page. Let's figure out the direction of the force on wire 1 due to the field created by wire 2. So first, let's figure out what the field created by wire 2 looks like. Point your thumb in the direction of the current I2, so left to right. Curl your fingers around wire 2. Everywhere above wire 2, the magnetic field B2 created by the current I2 points out of the page. All right, now let's try to understand the force on wire 1 due to the field from wire 2. Current carrying wires experience a force in a magnetic field. That force is IL cross B. Point your fingers in the direction of the current, I1. Curl them out of the page in the direction of the field B2. I'm doing some gymnastics over here to try to do that. And your thumb points in the direction of the force on wire 1. You could go through a similar double right-hand rule to figure out the direction of the field B1 created by wire 1 and the corresponding force that results on the current I2 due to that field B1. And you would find that the force on wire 2 points upwards because the field due to wire 2 points kind of, or due to wire 1, I should say, points kind of into the page. So what you find when you combine all those things together is that there's a force per unit length between these wires. Mu naught I over 2 pi A, that's the field created by one wire, and IL times B is the field, is the force on the other wire. Combining all those things together, there's a force per unit length. This formula is on your formula sheet, and those forces will be attractive if the currents are in the same direction, or repulsive if the currents are in opposite directions. And so summarizing that, opposites repel. Remember with point charges and the force, the electric force between point charges, opposite sign charges attract each other. With currents, current carrying wires, and the magnetic forces that act between the wires, opposite currents repel each other, currents in the same direction attract each other. All right, so that's yet another manifestation, and that's kind of combining two things, right? The force on one wire, but due to the field created by the other wire. Let's take a look at an example of that. We'll go to page 214 in your booklet. And on page 214, there's some room for multiple choice question 9 from page 57. Page 214 and page 57. And that's the one at the top of the screen. I'll just give you a moment to read that one over. All right, so we've got two long straight wires, 15 centimeters apart, lying in the XY plane. The upper wire carries a current of 2.5 amps directed to the right. The lower wire carries a current 4.5 amps directed to the left. And the question is, what's the magnetic force on a 1 meter segment of the lower wire? So what's happening here, looking for the key words? We've got current carrying wires. We know they create magnetic fields. And we know magnetic fields exert forces on current carrying wires. So this is the force between two current carrying wires. I'm just going to go back into the course booklet and draw that scenario for us. We've got wire 1, let's call it I1, is 2.5 amps to the right. And we've got wire 2, 4.5 amps to the left. We want to find the force on a 1 meter segment of that lower wire. Now, I just noticed, and somebody else just messaged me in the Q&A, I just noticed that that formula for force per unit length isn't actually on your formula sheet. I'm going to show you how we can derive it. I'm going to go to your formula sheet here and just highlight the relevant formulas. So this should be on the second last page of your exam package. It's your formula sheet for this year. And I'm going to zoom in here on the section on magnetism. And I'm just going to highlight two important equations. One is the force on a current carrying wire due to an external magnetic field. And the other is the magnetic field created by a current carrying wire. Those are the formulas we have in our formula sheet. Let's go back in your course booklet and we'll derive the equation for the force per unit length between those wires. So in general, or from your formula sheet, F equals IL cross B, or the magnitude of the magnetic force on a current carrying wire is ILB sine theta. Theta is the angle between the magnetic field and the direction of the current. And the magnetic field created by a wire is mu naught I over 2 pi r, the distance away from the wire that you go. We want to find the force on wire 2. Where does that force come from? It's because there's a field, let's call it B1, created by the wire I1. Point your thumb in the direction of the current I1, so to the right. Curl your fingers around that wire. And what you find is that there's a magnetic field, B1, let's call it, into the page below wire 1. That magnetic field exerts a force on wire 2. So let's write that down. The force on 2 equals I2 L B1. The field created by wire 1 is exerting a force on wire 2. Let's substitute in for the strength of the field created by wire 1. There's a distance r between the wires. And so the force on wire 2 per unit length is mu naught I1 I2 over 2 pi r, the distance between the wires. That's the formula that I highlighted for you in your course booklet, sorry. That's not on your formula sheet, but you can see how easy it is to get. Find the field created by one wire and sub it into the equation for the force acting on the second wire. We know all those quantities, so we can go ahead and calculate this. And if we sub the numbers in, we can calculate this out. Mu naught is 4 pi times 10 to the minus 7. That's a constant of nature. I1 is 2.5 amps. I2 is 4.5 amps. And the distance between the wires is 15 centimeters. And if we calculate that out, we get 1.5 times 10 to the negative 5. That's newtons. And I'm just going to highlight in red here, right? This is actually newtons per meter, right? We've calculated the force per unit length on that wire. And the correct answer there is answer B. I'll just pause there and see if there's any questions about that one. Okay, so anytime you have two long parallel current carrying wires, there's going to be forces exchanged between them. Opposites repel. If the currents are in the same direction, the wires have a force towards each other. If the currents are in opposite directions, the wires have a force that pushes them apart. All right. In your course booklet, we're just going to go back and review what we've done so far. Let's go back to page 198. Section 7.12 on page 198. What I've done in section 7.12 on page 198 is to create a summary for you of all the different magnetic effects that we've studied so far. And I know that when I learned all this stuff for the first time, my head was literally spinning with all the different right-hand rules and all the different effects that we've talked about. So let's just summarize and review everything we've talked about magnetism so far. The first observation we had was that a long straight current carrying wire experiences a force due to an external magnetic field. And the magnitude of that force, IL cross B, the right-hand rule says point your fingers in the direction of the current, curl your fingers into the direction of the field, and your thumb points in the direction of the force. I can annotate that on here if you want. So your fingers curl into the direction of the magnetic field, and your thumb points in the direction of the force. Okay, that's the first manifestation of magnetism we learned about today. And by extension, if current carrying wires experience forces due to magnetic fields, that means if you get a loop of wire or multiple loops of wire, then that loop will experience a torque. And to calculate the torque, we use this formula, NIAB, or in its more general form, mu cross B. This magnetic dipole moment vector mu, NIA, really what it's accounting for is the number of turns of wire, the current in the wire, and the orientation of the loop. A is the cross-sectional area of the loop, but that magnetic moment vector is perpendicular to the plane of the loop. It accounts for the orientation of the loop. The loop will experience a torque that tries to align that magnetic moment vector with the magnetic field. All right. That's the second manifestation of magnetism we've learned about. Let's go on to the third one. Since current-carrying wires experience a force in magnetic fields, and since current is made up of many individual point charges, then it follows a single moving charged particle experiences a force due to a magnetic field. The force is at right angles to both the velocity and the magnetic field. And the right-hand rule would be point your fingers in the direction of the velocity vector, curl them towards the direction of the magnetic field vector, and your thumb points in the direction of the force on that point charge due to the magnetic field. If there's also an electric field present, then there will be an electric force as well. Watch out for negative point charges because the direction of that force flips in the opposite direction for a negative point charge. Okay. The next manifestation of magnetism we learned about is the magnetic field created by a current-carrying wire. And we use the Biot-Savart law to calculate the magnetic field created by current-carrying wires. We looked at a special case for straight current-carrying wires, and we're going to use the Biot-Savart law in a few long answer problems we're going to study. Most likely tomorrow, it looks like tomorrow morning, and that will help us understand how to use the Biot-Savart law in a more general way. That's the magnetic field created by a current. And the last manifestation of magnetism we learned about is the forces exchanged between two long parallel current carrying wires. Each wire creates a field that exerts a force on the other wire. And we had that notion of opposites repel. I'm just going to annotate this in a slightly different way. All of these things are effects of magnetic fields on objects. If you know what the magnetic field is, you can calculate the effect it will have on a current carrying wire or a loop or a single moving charged particle. Item 4 is the cause of magnetic fields. Currents create magnetic fields. And item 5 is really a combination of those, right? It's the fact that one wire creates a field that exerts a force on the other wire and vice versa. And zooming back out to the beginning when we started talking about magnetism today, remember we were talking about this complementary behavior, the idea that currents experience forces due to magnetic fields, but currents also create their own magnetic fields. There's this kind of complementary behavior. There's a cause and effect behavior involved there. So hopefully that helps to summarize that for you. Let's go over to the next page, and page 199. And I tried to summarize that in a slightly different way, and this time with this notion of cause and effect. And I've summarized the important equation that governs each of those different scenarios, and I've also summarized the right-hand rule that's involved. I won't go through that whole table in detail, right? It basically summarizes the information from the previous page in maybe a more concise way, but I'll let you guys go back and review that. And you might want to study that table or study the page before. Just make sure you're comfortable with each of those 5 different scenarios. And for magnetism, the trick is when you're at your exam, you have to be able to look at a question and ask yourself, which of those 5 scenarios are we talking about? Which manifestation of magnetism is this question asking about? Once you figure that out, then you know which formula to use, and then you know which right-hand rule to use. Hopefully you guys find that helpful. That's something that I had to learn to do myself when I was in my electricity and magnetism courses, just to keep my head screwed on straight, because there's just so many things happening with magnetism. All right, let's take a look at a long answer problem on magnetism. We're going to go to page 221 in your booklet. Page 221. And there's some room there to look at the long answer problem that's on page 23 of your exam package. Page 221 and page 23. Give you guys some time to read this whole problem over before we start working through it together. Okay, there's a lot going on in this problem. We've got a proton. We're given its charge and mass at the very bottom of the question. We're told the speed that it's moving at and that it enters a field region where there's a magnetic field in the Z direction. In part A, if the proton crosses the positive y-axis while moving in the positive x direction, so you can see its velocity vector here, the question is, what's the magnitude and direction of the force acting on the proton? Where does that force come from? It's the force on a moving point charge due to the magnetic field. We can calculate that out. In part B, if the motion is centered on the origin, where will it cross the positive y-axis again? So we'll have to calculate that out. How many times will it cross the positive y-axis in 1 second? So we get the sense that this proton is going to undergo some motion. We know that moving charged particles and magnetic fields move in circular paths. So we'll have to calculate the radius of that circular path and the period of that motion. Now, something interesting happens when we look at part C, D, and E. What if there's also an electric field in the Z direction? The question is, what's happening? There's going to be a total acceleration. We need to describe the path. How does the electric field affect that path? And the Z component of the displacement after a certain period of circular motion. So there's lots going on here. This is a charged particle moving through a magnetic field, at least in part A and B. We can go back to our course booklet and start calculating some things about this. In part A, we want to get the magnitude and direction of the force on this proton. The force on a moving charged particle in a magnetic field, QV cross B. V and B are perpendicular to each other. So in terms of calculating the magnitude of that force, QVB sine theta, theta is 90 degrees, so that just becomes 1. And we can calculate the magnitude of that force, QVB. We're given the speed of this proton, 3 times 10 to the 5, and the magnetic field strength, 0.4 Tesla, and the magnitude of that force is 1.92 times 10 to the negative 14 newtons. What's the direction of the force? We have to use the right-hand rule to figure out the direction. Point your fingers of your right hand in the direction of the velocity vector, so to the right. Curl them into the direction of the magnetic field, B, so that's out of the page. And your thumb points down. The direction of the net resulting force at the instant that this proton enters the field region is down. So if you want to fully answer this part A, the direction of that force is in the negative y direction, so the minus j hat direction. That should be sufficient to get full marks for part A. And if that's the direction of the force on this proton as it enters that field region, then it's going to curve. It's going to curve in a circular path. And let's go ahead and calculate the radius of that circular path. If the magnitude of the net force on this proton is QVB, and that's equal to the net force in circular motion, mv squared over r, then the radius of the circular path is mv over qb. We can calculate that radius. We know the mass of the proton and its speed, its charge, and the strength of the magnetic field. And from that, we get a radius, 7.83 times 10 to the negative 3 meters. Now we're told that the proton has a motion that is centered on the origin. And if that's the radius of the circular path, that's r right there, and that's another r right there. So in other words, this proton crosses the positive y-axis at y equals plus 7.83, and it crosses the negative y-axis at minus 7.83. So to answer that properly in words, you could say something like this. Therefore, the proton crosses the y-axis at plus and minus 7.83 times 10 to the negative 3 meters. Or if you show your picture, that's probably sufficient as well. Something like that should get us full marks for part B. Now, oh, sorry, full mark for part B. There's another question in part B, and that is how many times does it cross the y-axis per second? In other words, what's the period of this motion? And to calculate the period of this circular motion, consider that speed equals distance over time in general. And the circumference of a circle is 2 pi r. So if it takes one period, big T, to go around the circle once, you can relate the speed and the period. The period is 2 pi r over v. And we know what those quantities are. We can calculate out the period and we get 1.64 times 10 to the negative 7 seconds. You could also calculate the frequency of this motion. That's 1 over the period. And that's 6 times 10 to the 6 hertz. I think either of those would be sufficient to get the rest of the full marks for part B. You could tell them the period of the motion or the number of times per second. In other words, the frequency of the motion. That should be sufficient to get full marks. That's something that's known as the cyclotron frequency. You might have seen that term before in your textbook or course notes. So we've done part A and part B. Now, in part C, something else happens. In part C, now there's an electric field present as well. And I'm going to draw another picture of the situation for part C. I'm going to try to draw this one a little bit bigger, make it a little bit more clear. So the magnetic force acting on this proton causes it to go in a circular path. But we're told in part C that there's also an electric field present. And we're told that that electric field points in the Z direction. So there's also an electric field pointing out of the page. And the question is, how does that change the motion? In general, if there's both an electric and a magnetic field, the force on that charge will be QE plus QV cross B. This is what we call the magnetic force, and this is the electric force. And let's annotate on our diagram what direction those forces are in. We already found out in part A that the magnetic force on that proton is downwards as it enters that field region. What's the direction of the electric force on that proton? QE, positive point charges accelerate in the direction of the electric field. So the electric force on that proton is out of the page. The magnetic force causes the proton to go in a circular path in the plane of the page. The electric force causes the proton to accelerate out of the page. So what's happening here? The proton's going to start spiraling up out of the page along the Z-axis, out of the page towards you. In part C, we want to calculate that acceleration. And we can calculate that from Newton's second law. The acceleration of the proton is QE over m. Let's plug the quantities in and calculate that out. The electric field is given 1 times 10 to the 4 volts per meter or newtons per coulomb, and the mass of our proton. And when we calculate that out, the acceleration of this proton is 9.6 times 10 to the 11 meters per second squared, and that's in the plus k hat direction. In other words, out of the page towards us. So this is something interesting to just pause and talk about before we go further. This is the Lorentz force, right? The combination of an electric force and a magnetic force on a charged particle that's moving through a region where there's mixed electric and magnetic fields. And notice something interesting. The magnetic force does accelerate that proton. It causes the proton to change direction, but it doesn't change the proton's speed. It doesn't change its kinetic energy. So the magnetic force doesn't do any work. But it does provide an acceleration. It does result in a force. Whereas the electric force does do work. And it's causing that electron to accelerate. And to figure out the direction of that acceleration, notice that we have a positive point charge and we have an electric field that we're told is in the plus Z direction out of the page. Positive point charges accelerate in the direction of the electric field. So out of the page in the Z direction. Okay. So that's kind of interesting. And we might be able to visualize that spiral path that that electron's going to take as it starts orbiting the Z axis, I guess, and spiraling up out of the page towards us. That's part C. So in part D, what we want to try to do is describe that motion. And it might be a little bit tricky to show this with a diagram. I guess if you wanted to, you could reorient this coordinate system. So if you were to put the x-axis upwards and the y-axis out of the page towards you, then the z-axis would point this way. And if you were to do that, is that the right way to visualize it? Yeah, our proton's crossing the y-axis, right? It's kind of orbiting around the y-axis, but it's actually going to spiral along the z-axis like so. So one way to do that is with that diagram. That's kind of hard to visualize. So you might even write it something like this. The magnetic force causes circular motion around the z-axis. The electric force causes acceleration along the z-axis. So therefore, this is like a spiral centered on the z-axis. Yeah, there's a couple of questions in the Q&A about how to draw this or visualize it, and I agree it's a little bit tricky to draw and visualize, right? Some combination of a drawing and some words like that should be enough to get us full marks there. Now, there's an interesting question in part E, and that is to figure out what the Z displacement is after one period of the motion. So what's happening here, if we consider the motion along that spiral path, it takes a certain amount of time to go around one circular orbit of the z-axis, but in that same amount of time, a certain displacement along the z-axis has happened. In other words, there's a certain pitch to that spiral path, and we can calculate what that pitch is because we know what the acceleration along the z-axis is. And if we use kinematics for that, the z coordinate as a function of time is z naught plus v naught zt plus a half az t squared. That's kinematics. Now this particle starts in the xy plane, and as it enters that region, it doesn't have any speed in the Z direction yet. And so Z at t equals big T, after one revolution, one orbit, we can calculate where it is. And it's at 1.29 times 10 to the negative 2 meters in the Z direction. Now, there's something important, I think, that we didn't capture in our diagram or a description in part D. And that's the fact that there's a constant electric field in the Z direction, meaning that there's a constant acceleration in the Z direction. And I think that means that the pitch of this spiral keeps getting bigger and bigger. I'm going to try to capture that better in my drawing here. You guys can see that I'm not great at drawing at the best of times on my little tablet here, but let's try to capture that. This thing orbits, but the pitch gets bigger and bigger and bigger. And the reason is that there's an acceleration in the Z direction that causes that pitch to kind of increase with time. The radius of that spiral is constant, and that's because of the magnetic field, the orientation of the magnetic field and the velocity vector. All right, there's a question here in the Q&A. Why don't we include the magnetic force for acceleration if magnetic force does cause acceleration? I'm really, really glad you asked that question. It's a really good one. I'm just going to scroll up to the top here to answer that again. Just focusing on the very top left of the screen here. Notice that the electric force is in the same direction as the electric field. Q is a positive quantity. The electric field vector points in the Z direction. So the electric force and the resulting acceleration is in the Z direction. Okay, so the electric field accelerates the point charge. But what about the magnetic force due to the magnetic field? There's a vector cross product here. The magnetic force is perpendicular to both the velocity and the magnetic field. That's the result of the vector cross product. Another way of saying that, you have acceleration perpendicular to velocity. The acceleration changes the direction of the velocity, but it doesn't change its speed. That's uniform circular motion. So when we're trying to calculate the acceleration of this particle, what we're really looking at is its acceleration in the Z direction due to that electric field. If you wanted to, you could calculate the radial acceleration due to the magnetic force, but notice that that radial acceleration would have a constant magnitude, but a continually changing direction. That radial acceleration is a centripetal acceleration. It's the net resulting acceleration from that circular motion. So I didn't include it in this part of our solution. Hopefully that answers your question. All right, so that's the Lorentz force and the cool patterns that you can create from charged particles. We're at 4 o'clock here. We're going to pause here for the day, and we're going to get started again tomorrow at noon. And the plan for tomorrow is to go through more long answer problems on magnetism. We're going to cover everything about complicated forces, how to calculate magnetic fields with the Biot-Savart law. And then partway through tomorrow, we'll get into electromagnetic induction and Faraday's law. All right, guys, let's wrap it up there for today, and I'll see you guys tomorrow at noon. Thanks a lot.